far below the surface of the Pacific Ocean, where sunlight has never reached and the pressure is strong enough to crush a submarine hull. Scientists lowered cameras into a part of Earth they believed was nearly empty. Instead, something moved. In 1977, researchers exploring the seafloor near the Galapagos Rift found entire ecosystems clustered around cracks in the rock. Giant worms, white crabs, mollusks, creatures living in total darkness beside water hot enough to melt lead, and the discoveries never stopped. In 2025, a Chinese submersible found thriving animal communities nearly 10 kilometers below the ocean surface, deeper than any complex ecosystem ever observed before. Worms almost a foot long, sea cucumbers, mollusks gathered around chemical seeps in a place science once considered impossible for life. The deepest parts of the ocean are colder than Antarctica, darker than space, and buried beneath pressures more than 1,000 times stronger than the air around you right now. And yet something survives there, not just microbes, entire ecosystems. Some animals living in the deep have no mouths, no stomachs, and no digestive systems at all. Others survive beside near-boiling hydrothermal vents by farming bacteria across their own bodies. There are fish with eyes the size of dinner plates, hunting in darkness no human being has ever naturally witnessed. And beneath the seafloor itself, inside solid rock, microbial life is still alive and dividing so slowly that some cells may reproduce only once every 10,000 years. We have directly explored only a tiny fraction of the deep ocean floor. Nearly every expedition discovers species completely unknown to science. In this video, we descend into the deepest ecosystems on Earth and follow the discoveries that changed what scientists thought life itself was capable of becoming. But before we begin, I'm curious, is this your first time here, or have you been down this rabbit hole with us before? Let me know in the comments. Now, let's descend into the darkest ecosystems on Earth. Long before cameras drifted through trenches or submersibles settled onto volcanic seafloor, the deep ocean existed in scientific thought as a kind of fading absence. The farther the water descended, the more life was expected to thin out, dissolve, and finally disappear altogether into cold sediment and darkness. For generations, this was not treated as speculation. It was treated as simple arithmetic, as obvious as gravity or the tides. The reasoning appeared almost impossible to argue against. Nearly every visible ecosystem on Earth depended, directly or indirectly, on sunlight. Forests leaned toward it, plankton bloomed beneath it, entire food webs rose from microscopic plants drifting near the illuminated surface of the sea. But sunlight does not travel far through water. By roughly 200 meters, the ocean has already swallowed almost all of it. Beneath that threshold, the descent continues into a blackness so complete that day and night become meaningless, and so a picture formed. Whatever existed below must survive only on leftovers from the world above. Tiny flakes of dead plankton, fragments of decaying animals, drifting waste, slow particles of biological debris sinking through kilometres of empty water. By the time those remnants reached the abyssal floor, they were expected to contain almost no useful energy at all. Enough, perhaps, for scattered microbes, enough for a few pale scavengers buried in mud, but certainly not enough for abundance. In the 19th century, British naturalist Edward Forbes gave this belief a formal shape. In 1843, after studying marine life collected from relatively shallow dredging operations, he proposed what became known as the azoic hypothesis. Below roughly 550 meters, he argued, animal life ceased entirely. The deep ocean was an azoic zone, a region without creatures, without ecosystems, Without movement, the idea settled quietly into science because it fit the world people thought they understood. The deep sea was inaccessible, crushing, and hidden. Every practical limitation of 19th century exploration reinforced the assumption. Nets returned empty or damaged. Pressure distorted specimens hauled toward the surface. Vast regions of ocean floor remained physically unreachable. It was easier to imagine emptiness than complexity. Eventually, evidence began to fracture the theory itself. Expeditions in the late 1800s pulled strange animals from greater and greater depths. Brittle stars, worms, crustaceans, and soft-bodied organisms arrived on deck coated in mud from places once declared lifeless. Forbes's original boundary collapsed under accumulated observation, but the deeper assumption survived. The ocean floor was no longer considered entirely dead, only weakly alive. A sparse world, a biological afterthought. Creatures at depth were imagined as slow and isolated, enduring existence rather than flourishing within it. The abyss became a place of scarcity in the scientific imagination, populated by thin shadows of the energetic living systems closer to sunlight. That quieter assumption endured for more than a century because, on the surface, it still seemed reasonable. The deep ocean remained brutally cold. Pressure mounted to extraordinary extremes. Food appeared scarce. Every known principle of biology still pointed upward toward the sun as the central engine of life. What no one yet understood was that the ocean floor possessed its own energy sources, hidden beneath the crust itself. Chemical reactions deep inside the earth were feeding entire ecosystems, independent of sunlight, independent of seasons, independent even of the surface world above. While scientists imagined the abyss as an ecological desert, vast communities had already been living there for millions of years around volcanic fissures. Methane seeps, whale skeletons, and chemical gradients invisible from above. The distance between assumption and reality was immense. Not a small scientific correction, but a collapse of perspective. The deep ocean was never an empty graveyard at the bottom of the planet. It was a living world operating by rules that surface biology had barely begun to recognize. A parallel system hidden beneath kilometres of water, carrying on in darkness, while almost no one on land imagined that such a thing was possible at all. Metal cables slipped downward through the Pacific in February of 1977, vanishing slowly beneath the research vessel Noor as the camera sled Angus descended toward the Galapagos Rift. On deck, geologists and geochemists watched instrument readings flicker across monitors in the cold night air, waiting for data from a region of seafloor that science still regarded as largely uneventful. The expedition had not been searching for thriving ecosystems. It had been searching for the mechanics of the Earth itself, for fractures in the crust where tectonic plates drifted apart in darkness far below. At roughly 2,500 meters beneath the surface, the ocean floor should have been uniformly cold. Water at that depth hovered only a few degrees above freezing, part of a stable, deep environment thought to change very little across vast distances. But as Angus moved over the Rift Valley, the temperature readings abruptly surged upward. Near freezing became impossibly hot within moments. Instruments registered temperatures exceeding 400 degrees Celsius in water that remained liquid beneath the immense surrounding pressure. The data made little immediate sense. Heat on the seafloor was expected in theory near spreading ridges, but not like this, and certainly not accompanied by what appeared in the photographs when the sled finally returned to the surface. Robert Ballard later described the moment quietly. Scientists gathered around the images in near silence, trying to understand what they were seeing. Rising from the seafloor was shimmering water, distorted by heat, like air wavering above desert stone. The ocean floor itself appeared cracked open, venting mineral-rich fluid directly into the surrounding darkness, and around those openings, life. Not scattered animals surviving at the margins, but dense communities gathered in astonishing abundance. Clams larger than dinner plates lay packed together across the rock. Pale crabs moved between them in clusters. Strange white fish drifted through the heated water. Tall red-tipped organisms swayed in thick colonies, resembling underwater flowers rooted around the fractures in the crust. The photographs seemed to violate the biological logic that had guided marine science for generations. No sunlight had ever reached this place. No photosynthetic food web connected it to the illuminated surface ocean above. Yet the seafloor around the vents supported one of the richest ecosystems ever discovered in the deep sea. When the submersible Alvin descended for direct observation later that same year, the reality became even more disorienting. The vent fields stretched across the volcanic terrain like living islands surrounded by barren basalt. Water erupted continuously from openings in the crust, carrying dissolved minerals and chemicals from deep within the earth. Animals crowded so densely around the vents that portions of the rock itself disappeared beneath layers of shells, tubes, and moving bodies. Ballard later compared the experience to processing a nonlinear equation, a sensation of confronting something that did not fit the existing shape of understanding. The discovery was immediately recognized as more than a biological curiosity. It altered the conceptual foundation beneath modern ecology itself. Then, only 2 years later, another expedition revealed an even more dramatic version of the same phenomenon along a separate mid-ocean ridge. Towering mineral chimneys rose from the seafloor like blackened stone spires, some reaching the height of buildings. From their openings poured jets of superheated fluid, thick with dissolved sulfides and metals, erupting upward in dark plumes that resembled smoke drifting through water. These formations became known as black smokers. Despite temperatures surpassing 400 degrees Celsius, the fluid did not boil. The crushing pressure of the deep ocean held it in liquid form, creating a chemical environment unlike anything on the surface world, and again, life gathered there in impossible density. Species unknown to science appeared faster than researchers could classify them. Worms, mollusks, crustaceans, fish, and microbial communities occupied the vents in layered ecosystems powered entirely by the chemistry rising from beneath the Earth's crust. Not one organism in those communities depended directly on sunlight. Entire generations had lived and died in darkness, while the surface world remained unaware they existed at all. The textbooks had not simply expanded, they had broken open. Across the surface of the earth, an invisible transaction repeats endlessly beneath leaves, within algae, across forests, wetlands, grasslands, and the bright upper skin of the sea. Light arrives from the sun, and living cells capture it. Every grazing animal, every predator, every drifting organism higher in the food chain inherits that stored sunlight indirectly, carried upward through layers of consumption and decay. For centuries, biology understood this relationship as the central rule beneath all complex life. Even the oceans followed it. Near the surface, microscopic phytoplankton floated through illuminated water, converting sunlight into organic matter that fed the marine world above and below them. Everything farther down depended ultimately on that distant brightness filtering from the sky, which meant the communities surrounding hydrothermal vents presented a problem far deeper than unusual animals clustered around volcanic rock. The problem was energy. The vent ecosystems were too dense, too active, too biologically productive to survive on drifting scraps alone. Giant clams grew in crowded beds. Worm colonies expanded rapidly around fissures in the crust. Crabs and fish moved constantly through the heated water. The amount of living tissue gathered around the vents exceeded what the slow rain of dead material from the surface could reasonably support. Some other engine was operating there, hidden beneath the visible forms of the animals themselves. The answer emerged from organisms so small they remained almost invisible even within the discovery that transformed marine science. Thin films of bacteria coated the rocks near the vents. Microbial mats spread across mineral surfaces in pale layers. Inside the tissues of larger animals, additional microbes lived in extraordinary abundance, woven directly into the biology of their hosts. Decades earlier, in the 1800s, Russian microbiologist Sergei Winogradsky had proposed the possibility of organisms capable of sustaining themselves through chemistry alone. While studying soil bacteria, he observed that certain microbes could derive energy not from sunlight, but from inorganic chemical reactions. At the time, the idea remained largely confined to microbiology. No one imagined an entire ecosystem could rest upon it, but on the deep ocean floor, chemistry had replaced sunlight entirely. Hydrothermal vents released vast quantities of hydrogen sulfide into the surrounding seawater, alongside methane, dissolved metals, carbon dioxide, and other compounds toxic to most surface organisms. Hydrogen sulfide carried the sharp scent associated with rotting eggs at the surface world above, yet here it drifted continuously from openings in the Earth's crust beneath crushing pressure and perpetual darkness. Specialized bacteria and archaea evolved to use that chemistry directly. Instead of capturing photons from sunlight, they harvested energy from chemical bonds. Through chemosynthesis, they converted inorganic compounds into organic material, building living tissue from the raw chemistry pouring upward through the vents. These microbes became the true foundation of the ecosystem. The great vent animals were not independent survivors clinging to volcanic rock. They were extensions of microbial metabolism, living atop an unseen biological engine powered by the earth itself. Some animals grazed directly on bacterial mats coating the seafloor. Others carried entire microbial colonies inside their own tissues, forming partnerships so intimate that one organism became inseparable from the other. The vents existed where two radically different worlds collided. Superheated fluid surged upward from beneath the crust, while near freezing seawater pressed downward around it. Between those extremes formed steep chemical gradients, invisible boundaries rich with unstable compounds and stored energy. The microbes occupied those boundaries the way forests occupy fertile soil or plankton bloom beneath sunlight. In surface ecosystems, plants and algae transform solar energy into life. In the deep vent fields, bacteria transformed geological energy instead. The implications spread quietly outward through biology, geology, and eventually astronomy itself. Life no longer appeared chained exclusively to sunlight or even to the surface of a planet. It could emerge wherever chemistry, liquid water, and usable energy intersected, even in darkness untouched by any star. Far below the waves, hidden for millions of years beneath pressure and volcanic heat, the Earth had been running a second kind of biosphere all along, one that drew its energy not from the sky above, but from the restless planet beneath it. Among the crowded mineral towers surrounding hydrothermal vents, there are forests that do not sway with tides in the familiar way of kelp or coral. They rise vertically from volcanic stone in pale clusters, long white cylinders packed tightly together, their bodies tipped with soft crimson plumes that unfurl into the heated water like drifting banners. Seen from a distance through submersible lights, they resemble oversized flowers rooted in the sea floor. though every structure in them belongs not to a plant, but to an animal. Riftia pachyptala, the giant tube worm, became one of the defining organisms of the vent discoveries because almost nothing about its biology aligns comfortably with ordinary expectations of animal life. A full-grown individual can reach nearly 3 meters in length. Most of the body remains hidden inside a protective tube secreted from organic material, white and parchment thin, anchored directly onto the unstable volcanic terrain surrounding active vents. Only the upper red plume extends outward into the surrounding water, exposed continuously to currents rich in dissolved chemicals. That plume functions as a gill, though even that word feels slightly insufficient for what the structure accomplishes. Blood flows through the feathery tissue in enormous volume, carrying oxygen, carbon dioxide, and hydrogen sulfide inward from the surrounding seawater. The red color comes from specialized hemoglobin molecules, unlike those in human blood, capable of binding both oxygen and sulfide simultaneously without poisoning the animal itself. And yet the most extraordinary feature of Riftia is hidden deeper inside the tube. It has no mouth, no stomach, no intestine, no digestive tract of any kind. An adult giant tube worm possesses none of the structures normally associated with eating because an adult giant tube worm never eats in the conventional sense at all. During its larval stage, drifting through the water column almost invisibly, it briefly develops a simple mouth and digestive system. In that early phase of life, it absorbs free-living chemosynthetic bacteria from the surrounding seawater. Then, as the worm settles near an active vent and begins to mature, those temporary feeding structures disappear completely. The mouth seals shut forever. Inside the worm's body, however, the captured bacteria multiply in astonishing abundance. A specialized internal organ called the trophosome becomes densely packed with symbiotic microbes, eventually housing roughly 285 billion bacterial cells within a single adult animal. The worm itself becomes less an independent organism than a living support structure for microbial metabolism. The bacteria process the hydrogen sulfide delivered through the worm's bloodstream and convert it into organic compounds through chemosynthesis. Those compounds then nourish the worm directly. Food is no longer gathered from the outside environment through hunting or grazing. It is manufactured continuously inside the body itself. The arrangement is so productive that Riftia grows at extraordinary speed for a deep-sea invertebrate. Some individuals can add nearly 85 centimeters of length in a single year, transforming bare volcanic rock into dense biological colonies within surprisingly short periods of time. Around active vent systems, thousands of worms may stand together in crowded assemblages, their red plumes extending outward into mineral-rich currents flowing through the darkness. But the stability of that world depends entirely on the restless geology beneath it. Hydrothermal vents are temporary features. Magma shifts below the crust, fractures seal or reopen, chemical flows migrate unpredictably across the seafloor. When venting activity weakens or stops, the surrounding worm colonies begin to die with startling speed. Without hydrogen sulfide circulating through the water, the bacterial symbionts can no longer produce energy. The entire living structure collapses from the inside outward, sometimes within only a matter of hours. Yet the disappearance is never entirely final. Throughout the surrounding ocean, microscopic larvae continue drifting silently through the currents, carried across immense distances in darkness. Sensitive to chemical traces in the water, they search constantly for new fissures opening in the crust below. When fresh volcanic surfaces begin releasing sulfide once again, new colonies settle, grow, and rise from the rock like pale towers, returning to a landscape that never truly remains still. Along the outer walls of hydrothermal chimneys, where mineral-rich water surges upward from beneath the crust in continuous torrents, there are narrow regions where temperature changes with astonishing speed. A few centimeters can separate water cold enough to numb exposed equipment from water hot enough to destabilize the chemistry of living tissue itself. Within those unstable borders, clinging directly to the black volcanic structures, lives a small gray animal that spends its entire existence balanced between those extremes. Alvanella pompejana, more commonly known as the Pompeii worm, was identified in 1980 by French researchers Daniel Desbruyères and Lucien Laubier, only a few years after hydrothermal vent ecosystems first entered scientific awareness. Its name came from Pompeii, the Roman city buried beneath volcanic ash after the eruption of Vesuvius, an echo of the environment where the animal itself survives. Fixed permanently against underwater volcanic stone deep beneath the Pacific. The worm is not especially large. Most individuals measure roughly 13 centimeters in length, their segmented bodies tucked inside protective tubes attached to the chimney surface. From the opening extend scarlet tentacle-like structures that wave gently in the surrounding currents, gathering oxygen from the seawater moving past. What transformed Alvanella from a biological curiosity into one of the most extraordinary animals on Earth was not its appearance, but the conditions measured around it. The rear portion of the worm's body remains pressed close against vent fluid approaching 80 degrees Celsius, temperatures that would rapidly destroy the proteins and membranes of most multicellular organisms. Yet the worm's head projects outward into surrounding seawater closer to 22 degrees Celsius. Across the length of a single animal exists a thermal gradient so extreme that it resembles two entirely different environments compressed into one narrow living space. For years, marine biologists debated whether any complex animal could truly survive sustained exposure to such heat. Then, in 1998, research led by marine biologist Craig Carey confirmed what earlier observations had suggested. Alvanella pompejana possessed the highest known heat tolerance of any animal yet studied, surpassing even desert insects adapted to the hottest terrestrial climates. Part of that resilience appears to come from something growing directly across the worm's own back. Seen closely, the surface of Alvanella looks almost furry, coated in a pale gray fleece that shifts softly in the surrounding water. But the material is not hair, skin, or external tissue in the ordinary sense. It is alive. Dense colonies of bacteria grow across the worm's body, supported by mucus secreted through specialized glands beneath the skin. The worm cultivates microbes on itself, the way shallow reefs cultivate algae beneath sunlight. Those bacterial colonies may serve several purposes simultaneously. Researchers suspect they help buffer the worm from abrupt thermal stress, forming a living insulating layer between the animal and the unstable temperatures surrounding it. Some evidence also suggests the microbes may assist in processing toxic chemicals released by the vents, reducing environmental stress across the worm's surface. At the molecular level, the bacteria possess enzymes capable of functioning at temperatures that would cause comparable enzymes in surface organisms to unravel and fail completely. Proteins that normally lose their structure under intense heat remain stable here, folded and active within an environment approaching the limits of known animal biology. That stability has drawn interest far beyond marine science. Heat-resistant microbial enzymes from extreme environments have become valuable in biotechnology and industrial chemistry, where high temperatures often destroy ordinary biological compounds. The deep ocean, once imagined as biologically barren, has quietly become a reservoir of molecular adaptations unavailable anywhere else on the planet. Meanwhile, Alvanella continues its life attached to volcanic chimneys in darkness thousands of meters below the surface. It feeds, reproduces, and grows within conditions that once seemed fundamentally incompatible with animal existence. Around it, superheated vent fluid pours continuously from the Earth's interior, while mineral deposits slowly reshape the chimney walls beneath entire colonies of living organisms. Nothing in the worm's world remains stable for long except the chemistry itself, the endless exchange between heat, pressure, microbes, rock, and water. Yet within that shifting boundary, the Pompeii worm persists calmly, wrapped in its own living coat, anchored to the side of an underwater volcano at the edge of what life can endure. Far below the shifting surface currents, the ocean floor is fractured by ridges that wind across the planet for tens of thousands of kilometers, a continuous volcanic seam where tectonic plates slowly separate. Along those submerged mountain chains, seawater slips downward into cracks in the crust, descending through porous rock toward regions heated from below by magma. There, in darkness beneath immense pressure, the chemistry of the water begins to change. The first hydrothermal systems discovered belonged to what scientists later called black smokers. These vents form where seawater penetrates deep into newly forming oceanic crust, becomes superheated, and reacts with surrounding rock before rising upward again through chimney structures on the seafloor. During that underground journey, the water dissolves sulfides, iron, copper, zinc, and other metals from the volcanic rock itself. When the fluid erupts back into the near-freezing seawater above, those dissolved minerals precipitate outward in dense black clouds, giving the vents their name. The chimneys surrounding active black smokers grow slowly through continual mineral deposition. Layer after layer accumulates around the vent openings until some structures reach nearly 60 meters in height, towering over the surrounding seafloor like submerged industrial ruins. Their surfaces remain unstable and brittle, continually reshaped by heat, mineral growth, and collapse. Around their bases gather dense biological communities, not evenly distributed across the abyss, but concentrated tightly around the chemistry flowing upward from below. Tube worms cluster in pale forests against the rock. Pompeii worms coat the hotter chimney walls in gray patches. Shrimp gather in moving swarms near the fluid openings, while microbial films spread across every chemically active surface available to them. The vent fields feel less like isolated animals surviving at depth and more like entire living landscapes assembled around geological energy. Inside the black smokers themselves, temperatures can exceed 400 degrees Celsius without the water boiling. At the surface of the Earth, such temperatures would transform liquid water instantly into steam. But beneath kilometers of ocean, pressure suppresses that transition, allowing superheated fluids to remain liquid while carrying enormous quantities of dissolved minerals and chemical energy upward through the crust. For years, these volcanic systems appeared to represent the defining form of deep ocean chemosynthetic life. Then another type of vent was discovered, one operating through an entirely different geological process. In the Atlantic Ocean, along the mid-Atlantic ridge, researchers discovered a hydrothermal field unlike the dark sulfide towers already familiar from Pacific vent systems. The structures rising from the seafloor here were pale instead of black, their surfaces made not from metal sulfides but from calcium carbonate, white as weathered bone beneath submersible lights. Some stood in clustered formations, nearly 60 meters tall, forming immense carbonate spires across the ridge. The site became known as Lost City. Unlike black smokers, the chemistry driving Lost City did not depend primarily on magma chambers heating seawater from below. Instead, seawater reacted chemically with mantle rocks through a process called serpentinization. As water infiltrated deep ultramafic rock, mineral transformations released hydrogen and methane directly into the circulating fluids. The resulting vent water emerged highly alkaline, approaching a pH near 12, chemically closer to industrial cleaning fluid than ordinary seawater. Yet within those chimneys, microbial life flourished. Microorganisms colonized tiny pores and channels throughout the carbonate structures, feeding directly on hydrogen generated by the rock reactions themselves. Entire microbial ecosystems existed inside the chimneys, hidden within mineral walls built gradually through chemistry rather than volcanic eruption. Lost City altered the scientific meaning of hydrothermal ecosystems almost as profoundly as the first vent discoveries had altered biology decades earlier. Black smokers still depended on active magmatic heat beneath the crust. But serpentinization required only rock and water interacting under pressure. No nearby magma chamber was necessary. That distinction quietly expanded the map of where life might exist beyond Earth. Beneath the ice-covered oceans of distant moons, sunlight may never penetrate the water at all. Volcanic heat may be weak or absent. But if liquid water contacts reactive rock deep below the ice, chemistry alone may still generate energy gradients capable of supporting living systems. In the deep Atlantic darkness, the pale towers of Lost City continued rising slowly from the seafloor, built grain by grain through reactions occurring silently inside the planet itself, while microbial life persisted within their walls, nourished by stone, water, and chemistry alone. In many regions of the deep ocean, the seafloor appears still at first glance, a broad landscape of sediment, undisturbed by volcanic eruption or rising heat. Yet beneath some of those quiet plains, ancient organic material lies buried under layers of mud deposited over millions of years. As that material slowly decomposes deep underground, methane, hydrogen sulfide, and hydrocarbon-rich fluids begin migrating upward through cracks and porous sediments, moving gradually toward the ocean floor in slow, invisible currents. Where those chemicals emerge, another kind of deep ecosystem forms. These environments became known as cold seeps, though the name creates a slightly misleading image. The fluids themselves are not truly cold. They are simply not superheated the way hydrothermal vent fluids are. Temperatures around cold seeps remain close to the surrounding deep ocean, often only a few degrees above freezing, calm and stable beneath the pressure of the abyss. But chemically, the seafloor there becomes transformed. Instead of energy arriving from volcanic heat and sulfide-rich vent fluid, cold seep ecosystems draw their power primarily from methane rising upward from buried organic deposits below the sediment. Methane oxidizing bacteria and archaea gather first, coating the seafloor in thick microbial mats that spread outward in pale white or orange layers across the mud. These microbial communities convert chemical energy into organic matter through chemosynthesis, creating the foundation for larger organisms above them. The result resembles a distant parallel to hydrothermal vent life, familiar in some ways, yet entirely separate in origin. Enormous tube worms emerge from the sediment in dense clusters, though they belong to different lineages than the vent worms surrounding volcanic chimneys. Mussels gather in tightly packed beds. Clams bury themselves beneath the surface, while bizarre segmented polychaete worms move through the soft sediment around them. Many of these animals carry symbiotic microbes inside their own tissues, forming intimate biological partnerships shaped not by sunlight, but by chemistry rising from underground. Cold seep mussels provide one of the clearest examples. Inside their gills live methane-consuming bacteria that process chemical compounds directly from the surrounding environment and nourish the mussels from within. The arrangement mirrors the bacterial symbiosis found in vent organisms, yet evolved independently in separate ecosystems. Different animals, different geology, different chemistry, arriving gradually at remarkably similar biological solutions. In some seep regions, the geology produces something even stranger. Deep beneath the sea floor, ancient salt deposits sometimes dissolve into underground fluids, creating dense brines saturated with salt far beyond ordinary seawater concentration. When those brines emerge onto the sea floor, they settle into depressions without mixing into the surrounding ocean because the fluid itself is so heavy. The result is an underwater lake. Brine pools rest on the ocean floor with visible boundaries separating them from the seawater above, their surfaces rippling gently beneath deep currents. Submersible lights reveal shorelines, reflective surfaces, and shimmering distortions where the two fluids meet. Fish and crustaceans drifting too deeply into the pools often die quickly, overcome by the oxygen-free, hypersaline chemistry inside. Yet, along the edges of these toxic lakes, life gathers densely. Mussels line the margins in crowded colonies, feeding indirectly on methane, seeping upward around the pool boundaries. Microbial communities spread through the surrounding sediment, while chemical gradients form delicate transitional zones between the lethal brine and the seawater above. Even here, where the environment resembles something closer to industrial waste than ordinary habitat, biological systems continue arranging themselves around available energy. For decades, brine pools were considered rare features restricted mostly to isolated deep basins. Then, in 2025, researchers studying the Gulf of Aqaba near the Saudi coastline discovered brine pools surprisingly close to shore, barely more than a mile from land. The finding altered assumptions about where such environments could form, suggesting that chemically isolated ecosystems may exist in far more locations than previously imagined. Beneath calm water and soft sediment, the ocean floor continued, revealing hidden worlds assembled around invisible chemistry, ecosystems powered not by heat or light, but by slow underground currents carrying ancient carbon upward through the dark. High above the abyss, in the bright waters near the surface, the death of a whale begins a descent that may continue for weeks. A blue whale can weigh close to 180 tons, its body carrying vast reserves of carbon, oil, and organic matter accumulated over decades of feeding across entire oceans. When life leaves it, the immense body loses buoyancy slowly and starts falling through the water column deeper and deeper into darkness. Eventually, the descent ends. The carcass settles onto the seafloor with enormous stillness, sometimes on open sediment plains, sometimes against rocky slopes or trench walls, wherever gravity finally carries it. Around it, the deep ocean begins to reorganize itself almost immediately. The first arrivals appear within hours. Sleeper sharks circle through the darkness. Hagfish slip into soft tissue through openings in the skin. Rat-tail fish gather in hovering groups above the carcass, while crabs climb across the body in dense, moving layers. Over the following months, the whale becomes the center of a vast scavenger community. Flesh is stripped away steadily, not in sudden violence but through continuous feeding, bite by bite, organism by organism. A single large carcass can sustain this mobile scavenger stage for nearly 2 years. During that time, the surrounding seafloor changes from sparse sediment into one of the most concentrated feeding sites in the deep ocean. Eventually, the soft tissue disappears almost entirely, exposing the skeleton beneath. Then the second phase begins. Smaller organisms arrive in growing numbers. Polychaete worms spread through the sediment surrounding the bones. Tiny crustaceans and mollusks colonize the remaining organic material embedded within the skeleton and mud nearby. Nutrients released from the decaying carcass enrich the surrounding seafloor, allowing opportunistic species to establish dense local populations where little food had existed before. But the most extraordinary transformation occurs much later, deep within the bones themselves. Whale skeletons contain enormous quantities of oil-rich lipids trapped inside their structure. As anaerobic bacteria begin decomposing those compounds in the oxygen-poor environment of the deep seafloor, hydrogen sulfide is gradually released outward from the bones into the surrounding sediment. Slowly, the whale fall becomes chemically similar to a cold seep. Chemosynthetic bacteria colonize the skeleton, feeding directly on the sulfide generated by decomposition. Dense microbial communities spread across the bones and nearby sediment, forming the foundation for a new ecosystem powered not by sunlight or drifting organic debris, but by chemistry emerging from the whale itself. Mussels, worms, and other seep-associated organisms arrive to exploit the changing environment, some carrying symbiotic bacteria inside their tissues, much like the animals clustered around hydrothermal vents far away. A whale that once crossed the open ocean as one of its largest living inhabitants becomes, in death, a long-lasting source of geological style, chemical energy on the seafloor below. This sulfophilic stage can persist for decades. In large skeletons, chemosynthetic communities may survive for 50 years or more before the remaining lipids are finally exhausted. The bones continue supporting life long after every trace of flesh has vanished. As scientists began comparing species from whale falls with organisms from vents and cold seeps, unexpected evolutionary connections emerged. Several species appeared across all three environments. Genetic evidence suggested that whale carcasses may have functioned as temporary biological stepping stones across the deep ocean floor, allowing vent and seep organisms to disperse gradually between isolated chemical habitats over immense stretches of geological time. Long before industrial whaling reduced global whale populations, hundreds of thousands of large whales likely died and sank every year across the world's oceans. Their skeletons would have scattered across abyssal plains, continental slopes, and trench systems in every ocean basin, creating a shifting network of temporary chemosynthetic refuges separated by darkness and distance. The deep sea, so often imagined as empty, had been threaded together all along by the slow movement of enormous bodies descending from the surface world above. Even in death, the whale continued feeding life, not briefly, but for generations. Beyond the volcanic ridges, beyond the methane seeps and submerged chemical oases, the deep ocean opens into something far quieter. Vast abyssal plains spread across the planet beneath kilometers of water, soft sediment stretching outward in every direction until distance itself becomes difficult to imagine. These plains occupy most of the deep seafloor, lying roughly 4 to 6 kilometers beneath the surface, broad and nearly featureless under permanent darkness. There are no mineral chimneys rising from the crust here, no heated fractures, no rivers of methane leaking upward through the mud. The geology grows still, and yet life continues. The only significant energy reaching these plains drifts downward from the illuminated ocean far above. Marine biologists gave this constant descent a deceptively gentle name, marine snow, though nothing about it resembles frozen crystals or winter skies. It is a continuous rain of biological debris sinking through the water column every hour of every day. Dead phytoplankton cells fall first, followed by fragments of zooplankton, discarded mucus, fecal pellets, scales, decaying tissue, microscopic shells, and countless particles of organic matter produced in the bright upper ocean. As the material sinks, it is consumed repeatedly by organisms living higher in the water column. Copepods graze upon it, gelatinous animals trap it, bacteria decompose it continuously during the descent. By the time the remnants finally settle onto the abyssal floor, most of the original energy has already been stripped away. What arrives below is thin, scattered, and nutritionally poor. By energy availability alone, the abyssal plain ranks among the most food-deprived environments on Earth. Large animals may spend months or years waiting for substantial nourishment to appear. Every drifting fragment matters. Every molecule of carbon becomes valuable. Still, the sediment remains alive. Sea cucumbers dominate many abyssal regions so thoroughly that they form the majority of visible animal life across the seafloor. Some species, informally called sea pigs, move slowly over the mud on short tube feet, their swollen bodies inflated slightly above the sediment as they feed. They process enormous quantities of seafloor material, swallowing mud continuously and extracting whatever traces of organic matter remain hidden inside it. In some locations, these soft-bodied holothurians account for more than 90% of the visible biomass across the plain. Entire landscapes appear populated almost exclusively by drifting, feeding sea cucumbers crossing the sediment beneath the dark water above. Elsewhere, giant isopods move slowly across the seafloor like relics from another geological age. They resemble terrestrial woodlice enlarged to improbable scale, armored crustaceans reaching nearly half a meter in length. Their segmented bodies and compound eyes remain recognizably familiar despite the immense depth where they live. Food arrives so unpredictably in the abyss that giant isopods evolved extraordinary patience. After feeding heavily on a carcass or concentrated organic deposit, they may survive for years without another substantial meal. Their metabolism slows to match the scarcity surrounding them, conserving energy within a world where abundance rarely appears. Across the plains, brittle stars extend delicate arms above the sediment to capture drifting particles from weak currents. Deep sea urchins graze methodically across the mud. Carnivorous sponges anchor themselves to the seafloor, trapping small crustaceans instead of filtering dissolved nutrients from the water. Rat-tail fish hover silently just above the sediment, searching for any movement that might indicate edible material below. Every organism remains connected, directly or indirectly, to the slow descent from the surface world above. Unlike the vent ecosystems driven by geology beneath the crust, abyssal life still depends ultimately on sunlight, though by the time that solar energy reaches the plains, it has been transformed almost beyond recognition. It arrives not as light, warmth, or active growth, but as residue, fragments, and faint traces drifting downward through kilometers of darkness. And across that enormous desert floor, life adapts itself to scarcity with remarkable precision. Bodies grow slower, movements become economical, feeding turns continuous and patient. The abyssal plain does not pulse with concentrated biological abundance the way vent fields do. Instead, it breathes quietly on geological timescales, sustained by a perpetual drizzle of organic matter falling gently from a distant world of sunlight far overhead. In the deep ocean, scale often begins to detach itself from ordinary expectation. Creatures related to tiny coastal animals appear at depths of several kilometers, transformed into oversized versions of their shallow water relatives, as though evolution followed a different geometry beneath the pressure and darkness of the abyss. Some of the clearest examples crawl directly across the seafloor. Isopods exist in shallow water all over the world, and their terrestrial relatives are familiar to almost anyone who has lifted a damp stone from garden soil. At the surface, most are small enough to rest unnoticed on a fingertip, but in the deep sea, giant isopods move across abyssal sediment with thick segmented armor and heavy clawed legs, growing close to half a meter in length. Their bodies resemble magnified versions of ordinary woodlice, enlarged to proportions that feel strangely disproportionate against the empty seafloor around them. The same pattern appears among amphipods. Near coastlines, amphipods are often tiny hopping crustaceans measured in millimeters, drifting through seaweed or jumping across wet sand. Yet in the hadal depths, supergiant amphipods such as Alicella gigantea grow to more than 30 centimeters long. During a 2026 expedition near Japan, cameras filmed these oversized crustaceans feeding nearly 7 kilometers beneath the surface, their pale, segmented bodies moving slowly through trench sediments, where almost no sunlight has reached for geological ages. Then there are the cephalopods. For centuries, giant squid existed more comfortably in mythology than biology. Sailors described enormous tentacled animals beneath storm-dark seas, while fragments recovered from whale stomachs hinted at creatures far larger than any squid humans had directly observed alive. Modern research eventually confirmed that giant squid can exceed 13 meters in length, while colossal squid may reach even greater sizes, becoming the heaviest invertebrates on Earth. Yet, despite all the fascination surrounding them, live footage of colossal squid in their natural habitat did not exist until 2025. For most of human history, these enormous predators drifted through the deep mid-water completely unseen, their massive eyes adapted to detecting faint movements and distant flashes within darkness, hundreds or thousands of meters below the surface. Elsewhere in the water column, oarfish move vertically through the ocean like living silver ribbons, sometimes exceeding 8 meters in length. They remain the longest bony fish alive, though encounters with them are so rare that entire generations may pass without one being observed near the surface. No single explanation fully accounts for why gigantism appears repeatedly in deep ocean ecosystems, but several patterns seem to overlap. Food scarcity may favor larger bodies because bigger animals lose proportionally less energy to their surrounding environment. In places where nourishment arrives unpredictably, conserving energy becomes essential for survival across long periods between meals. The cold temperatures of the abyss also slow metabolism, allowing animals to grow gradually over extended lifespans while consuming relatively little energy at any one moment. Predation pressure changes as well. In shallow coastal ecosystems, animals face constant threats from fast-moving predators, limiting how long many organisms survive. Deep ocean environments often contain fewer predators overall, allowing some species to persist for decades and continue growing slowly throughout their lives. Dissolved oxygen levels may also contribute. Cold, deep water can retain more oxygen than warmer surface environments, potentially supporting larger body sizes in some species. But even this explanation remains incomplete because gigantism appears selectively rather than universally. Many deep-sea animals remain extremely small. Vast microbial communities dominate trench ecosystems invisible to the naked eye. Tiny worms, crustaceans, and gelatinous organisms continue thriving throughout the abyss. The deep ocean does not simply enlarge everything within it. Instead, gigantism emerges unevenly across unrelated groups, appearing again and again through separate evolutionary pathways. Crustaceans, squid, fish, and other lineages arrive independently at unusually large sizes under conditions still not fully understood. Beneath the surface world, where pressure remains immense and food drifts downward in scattered traces, evolution often seems to favor patience over speed, longevity over urgency, and bodies shaped less by abundance than by endurance across immense stretches of darkness and time. At the bottom of the Japan Trench, more than 8 kilometers beneath the surface, cameras lowered into the hadal darkness. In 2026, captured a small translucent fish moving calmly above the sediment. There was nothing monstrous about it. No oversized teeth, no armored scales, no dramatic silhouette emerging from black water. The animal drifted with soft, fluid motions, its thin fins trailing behind it like fabric suspended in still air. Yet this fragile-looking creature occupied one of the most extreme environments any vertebrate has ever survived. The fish belonged to the snailfish family, Lifforms, a group that has quietly become one of the dominant vertebrate lineages of the deep ocean. The individual filmed in the trench was recorded at roughly 8,336 meters beneath sea level, deeper than any fish ever directly observed alive. At those depths, pressure exceeds 800 times what exists at the surface. Every square centimeter of the animal's body experiences forces immense enough to crush conventional submarines without reinforced hulls. For most vertebrates, the problem extends far beyond simple compression. Under such pressure, the molecules forming cell membranes and proteins begin changing shape. Biological structures lose flexibility. Chemical reactions slow or fail entirely. Eventually, ordinary animal physiology simply stops functioning. And yet the hadal snailfish moves through that environment with apparent ease. Its body appears almost unfinished compared to shallow water fish. The tissues are gelatinous and lightly built, lacking the dense bones and heavy musculature associated with fast-swimming predators nearer the surface. Much of the skeleton remains reduced and flexible, allowing pressure to pass through the body more evenly rather than crushing rigid structures inward. Seen beneath submersible lights, the fish often looks ghost-like, faintly transparent against the darkness surrounding it. Inside those soft tissues, however, exists an extraordinary chemical adaptation. Hadal snailfish accumulate extremely high concentrations of trimethylamine oxide, commonly abbreviated as TMAO. The compound stabilizes proteins and cell membranes under immense pressure, preventing the molecular distortion that would otherwise render biological systems non-functional. Among known vertebrates, hadal snailfish contain the highest concentrations of TMAO ever measured. At the surface world above, the same compound contributes to the characteristic odor people associate with seafood and decaying fish. In trench snailfish, the concentration becomes so extreme that if brought rapidly to surface pressure, the smell would likely be overpowering. But within the hadal zone, the chemistry serves as a molecular shield, allowing delicate biological processes to continue beneath conditions once thought fundamentally incompatible with vertebrate life. Video footage from trench expeditions reveals that snailfish are not passive drifters suspended weakly in the water column. They hunt actively across the seafloor, feeding on amphipods and other small crustaceans moving through the sediment. Their movements remain controlled and deliberate despite the darkness and crushing pressure surrounding them. The hadal trenches are not temporary refuges for these fish. They are complete ecosystems where snailfish spend their entire lives. Eggs are laid within the trench. Larvae develop there. Adults reproduce and die there. Every stage of their existence unfolds inside an environment lethal to almost every other vertebrate lineage on Earth. The species Pseudoliparus swirei, formally described from the Mariana Trench in 2014, became one of the clearest examples of this adaptation to abyssal pressure. Yet, it represents only a small branch of a much larger evolutionary radiation. Snailfish now number more than 400 known species, making them the most diverse family of deep-sea fishes currently recognized. New members continue appearing regularly as exploration expands into deeper regions. In 2025, researchers from the Monterey Bay Aquarium Research Institute described 3 additional species, including the bumpy snailfish discovered more than 3 kilometers beneath the Pacific surface. Across trench systems and abyssal slopes, the family continues diversifying quietly in darkness, their bodies reshaped by pressure into forms that appear delicate but remain extraordinarily specialized. Beneath the deepest waters of the planet, where ordinary vertebrate biology begins to fail, the snailfish persists with soft translucence and steady movement, living proof that even the vertebrate body can be carried into the crushing interior of the ocean and still remain alive. When organic material sinks into the hadal trenches, it rarely remains untouched for long. A dead fish, a drifting jelly, fragments of whale tissue, even the remains of surface organisms carried downward through kilometers of water eventually settle onto the trench floor. And almost immediately, the sediment begins to move. Tiny, pale crustaceans emerge first. Amphipods dominate many hadal ecosystems so completely that fish often become secondary presences beside them. Related distantly to shrimp and sand hoppers, amphipods exist throughout the world's oceans in thousands of forms, most of them small and easily overlooked. But within the trenches, certain species gather in extraordinary densities around any available food source, forming swarms that ripple continuously across the seafloor like living weather. Researchers lowering baited camera systems into the Mariana Trench frequently observe the same sequence. At first, the sediment appears empty beneath the submersible lights, still and featureless under immense pressure. Then, scattered movements begin at the edges of visibility. Within hours, hundreds or thousands of amphipods surround the bait, covering it in restless layers of feeding bodies. The species Hirondelia gigas has been documented in concentrations exceeding 10,000 individuals within a single square meter around trench bait stations. Their pale, segmented forms pile across one another continuously, antennae flickering through the darkness while the entire swarm vibrates with motion. In places where food remains scarce and unpredictable, rapid discovery and rapid consumption become essential survival strategies. Unlike many larger trench organisms, amphipods reproduce quickly. Populations can expand rapidly when organic material becomes available, allowing them to exploit temporary resources before slower competitors arrive. Their biology has also become remarkably specialized for pressure. At hadal depths, ordinary cellular chemistry faces severe physical stress. Enzymes and membrane structures that function comfortably near the surface begin losing flexibility under immense compression. In most crustaceans, biological processes would slow or collapse entirely. But hadal amphipods possess molecular adaptations that keep their enzymes stable and functional even beneath pressures capable of deforming conventional biological structures. The trench environment does not merely tolerate these crustaceans, it appears to favor them. As primary decomposers of the hadal zone, amphipods occupy a critical position in trench ecosystems. They break apart sinking organic matter rapidly, shredding tissue and recycling nutrients back into the surrounding environment where microbes, worms, and other scavengers can continue processing the remains. Without them, much of the biological material reaching the trenches would persist far longer on the seafloor before decomposition progressed. Yet hidden within their tissues, scientists eventually discovered something else descending from the surface world above. In 2017, researchers analyzing hadal amphipods found unexpectedly high concentrations of persistent industrial pollutants inside their bodies. Chemicals such as polychlorinated biphenyls and brominated flame retardants, compounds associated with manufacturing and industrial waste, had accumulated within trench food webs at levels surpassing those measured in crustaceans from heavily polluted rivers and coastal systems. The finding carried a strange quietness to it. Some of the least visited ecosystems on Earth, regions deeper than Mount Everest is tall, contained chemical traces of human industry drifting downward from cities, factories, and surface oceans thousands of kilometers away. These pollutants descend slowly through marine food webs. Microscopic particles absorb toxic compounds near the surface. Small organisms consume them. Larger animals consume those organisms. Dead tissue sinks into deeper waters, carrying industrial chemistry downward over years or decades, until eventually the compounds settle into trench ecosystems where scavengers like amphipods absorb them again. The hadal trenches, despite their isolation, remain connected to the rest of the planet through gravity, chemistry, and time. And still, the amphipods continue feeding. Across the trench floor, they swarm over carcasses, fragments, and falling debris with tireless efficiency, processing the remains of the upper ocean beneath pressures that would crush almost any surface animal. In darkness, deeper than sunlight has ever penetrated, vast populations of small crustaceans maintain the recycling system that allows trench ecosystems to persist at all, turning death continuously back into usable life at the very bottom of the sea. Across large stretches of the abyssal plain, the seafloor appears almost empty at first glance. Sediment extends outward in muted grays and pale browns beneath cold water and immense pressure, interrupted only occasionally by scattered rocks or drifting animals crossing the mud. Then, slowly, certain shapes begin to emerge from the landscape itself. Low branching structures rise from the sediment like collapsed fans. Rounded discs cling to the seafloor beside shallow depressions. Irregular clusters of debris appear gathered into delicate architectures that resemble abandoned nests, mineral growths, or fragments of deteriorating sponge. For decades, many of these formations were overlooked entirely. They are xenophyophores, among the strangest organisms yet discovered in the deep ocean. Though they resemble piles of collected sediment, each structure is alive. Each one is a single, enormous cell. Not a colony, not a multicellular animal. One cell. Xenophyophores belong to a group of giant protists inhabiting abyssal and upper hadal environments throughout the world's oceans. Some grow more than 20 centimeters across, making them among the largest single-celled organisms ever recorded on Earth. Compared to an ordinary human cell, which measures roughly 1/100th of a millimeter in diameter, a mature xenophyophore expands to a scale hundreds of thousands of times larger. Inside that sprawling body, the biological organization remains fundamentally cellular. Some species contain a single nucleus. Others possess many fused nuclei, distributed through a branching internal mass of living material suspended within the structure. The visible form surrounding that living interior is called a test. Xenophyophores build these tests slowly from particles gathered directly from the seafloor around them. Sediment grains, sponge spicules, shell fragments, and microscopic mineral debris become cemented together into intricate constructions unique to each individual. No two appear entirely alike. Some resemble delicate lattices spread flat against the mud. Others rise upward into branching fans or tangled mounds. The abyssal plain offers very little physical structure for animals to shelter within, and xenophyophores quietly alter that emptiness simply by existing. Small crustaceans crawl across their surfaces. Worms shelter within their folds. Predators search around them for prey hidden inside the sediment beneath the tests. Even fish make use of them. Research conducted along the Costa Rican continental slope discovered snailfish embryos deposited deep within xenophyophore structures, protected inside the cavities of a single giant cell. In the stillness of the deep ocean floor, vertebrate eggs developed safely within an organism so biologically unusual that it barely resembles conventional life at all. Their relationship with the surrounding environment extends beyond shelter. Xenophyophores actively process elements dissolved in seawater and trapped within sediment, accumulating unusually high concentrations of barium, lead, and radium inside their bodies. The exact mechanisms remain only partially understood. Their biology appears deeply intertwined with the chemistry of the deep ocean itself, absorbing and redistributing materials across the seafloor through processes science is still mapping in detail. They are also remarkably effective colonizers. Following volcanic disturbances on the seafloor, fresh layers of ash may settle across abyssal environments, temporarily burying existing ecosystems beneath sterile sediment. Xenophyophores can establish themselves on these deposits within only a few years, potentially becoming the first large visible organisms to return after such events. Their sprawling tests then create new habitat across the recovering seafloor, allowing additional species to settle around them over time. In many ways, xenophyophores challenge the instinctive boundary between microscopic and macroscopic life. A single cell becomes architecture, a protist becomes habitat. Something structurally simple grows large enough to reshape portions of the abyssal landscape around it. And still, despite their size, they remain easy to overlook. Submersible lights drift across the sediment, and xenophyophores often resemble nothing more than irregular debris resting quietly on the mud. Yet inside those fragile structures, one enormous living cell continues processing minerals, gathering particles, sheltering embryos, and persisting beneath kilometers of dark water in conditions that only recently became visible to human eyes at all. Far beneath the last reach of sunlight, the ocean begins producing its own stars. At roughly 200 meters below the surface, daylight fades into dim blue twilight. By 1,000 meters, even the faintest residual photon from the world above has vanished into the water. The pressure deepens, the temperature falls, and darkness becomes complete. Yet the deep ocean is not truly dark. Flashes drift through the water column constantly. Soft pulses ripple beneath transparent skin. Thin lines of blue light appear and disappear in sudden spirals before vanishing again into blackness. Some glow steadily. Others ignite only for an instant, brief cold sparks suspended in the water. More than 3/4 of the animals inhabiting the deep midwater are capable of bioluminescence, the production of living light through chemical reactions inside their own tissues. No external energy source is required. Molecules called luciferins react with enzymes known as luciferases, releasing photons directly from the body itself. Across evolutionary history, this ability emerged independently, again and again, in completely unrelated organisms. Bacteria evolved it, jellyfish evolved it. Squid, crustaceans, worms, and fish all arrived separately at the same solution. Few biological inventions have appeared so many times. In the surface world, color dominates visual communication. In the deep ocean, where sunlight no longer exists, life turned instead toward self-generated light. Some species use it to disappear. Midwater fish, moving beneath the faintest traces of downwelling light, possess rows of glowing organs along their bellies. These photophores emit blue illumination calibrated precisely to match the weak light filtering from above. Seen from underneath, the fish dissolves into the brightness overhead, becoming nearly invisible to predators searching upward through the water column. Elsewhere, light becomes bait. The anglerfish drifts through darkness, carrying a modified dorsal spine extending outward from its head. At the tip hangs a luminous organ inhabited by symbiotic bacteria. Small animals drawn toward the glow approach what appears to be drifting prey or distant bioluminescent movement. Then the anglerfish opens its jaws. Squid transformed light into something even more intricate. Certain deep-sea species cover their bodies with thousands of light-producing cells, capable of shifting patterns across their skin in fractions of a second. Waves of illumination ripple along their bodies silently, flashing signals through water where ordinary color cannot exist. Entire visual languages unfold in darkness beyond human sight. For many gelatinous organisms, bioluminescence functions defensively. When touched or attacked, comb jellies and siphonophores may erupt into brilliant flashes. The sudden light does not repel predators directly. Instead, it appears to attract larger hunters nearby, turning the attacker's presence into its own danger. Marine biologists sometimes describe this strategy as a burglar alarm effect, one predator accidentally summoning another. The deeper researchers looked, the more common living light became. Continuous recordings taken over 2.5 years in the Mediterranean deep sea revealed seasonal blooms of bioluminescent activity lasting for weeks at a time. During these periods, flashes throughout the water column increased dramatically, linked closely to pulses of sinking organic matter descending from surface ecosystems above. Even in darkness beyond sunlight, the deep ocean remained connected to the living surface world through drifting carbon and biological timing. Surface productivity influenced patterns of light thousands of meters below, linking distant ecosystems through invisible chains of energy and decay. In many regions of the ocean, bioluminescence may be the most common form of communication, predation, camouflage, and defense, occurring anywhere on Earth. Vast populations of organisms spend their entire existence surrounded by signals made not from sound or color, but from chemistry transformed directly into cold blue light. And through the deep water, those signals continue endlessly. Tiny flashes pulse through darkness beneath the continents and oceans of the planet, carried by drifting animals that evolved their own illumination in a world where the sun disappeared long ago. Among the drifting lights of the deep midwater, one shape appears again and again in human imagination: a wide mouth lined with needle teeth, a dark, rounded body suspended almost motionless in black water. Above its head, a thin, glowing filament sways gently like bait, lowered into an endless night. The deep-sea anglerfish became an icon long before most people understood where it actually lived. Members of the order Lophiiformes inhabit some of the darkest regions of the ocean, where food arrives unpredictably and encounters between animals may be separated by enormous stretches of empty water. Their bodies reflect that scarcity. Females possess enormous jaws relative to their size, capable of swallowing prey nearly as large as themselves. Every feature appears exaggerated toward one purpose: seizing food whenever the opportunity appears. Extending from the head is the elysium, a modified dorsal spine ending in a fleshy organ called the esca. Inside the esca, live colonies of bioluminescent bacteria sustained by nutrients supplied from the fish itself. The bacteria generate the cold blue glow drifting before the anglerfish in darkness. The fish does not produce the light directly. Instead, it maintains a partnership with luminous microbes, exposing or concealing the glowing organ as needed, while the bacteria continue shining within it. Small fish, crustaceans, and squid approach the moving light through the darkness, drawn toward what appears to be drifting prey or distant bioluminescent movement. Then the jaws open. Yet the hunting strategy of the anglerfish is only part of what makes it so biologically unusual. Its reproductive system remains among the strangest known in any vertebrate lineage. In most deep-sea anglerfish species, the dramatic form familiar from photographs belongs exclusively to the female. She grows comparatively large, develops the luminous lure, and carries the massive mouth filled with recurved teeth. The male, by contrast, is tiny. In some species, he measures less than a centimeter long and weighs hundreds of thousands of times less than the female. His anatomy reflects an entirely different existence. Males possess oversized nostrils, highly sensitive to chemical traces drifting through the water. Their digestive systems remain poorly developed, incapable of supporting long, independent survival. They are not built for prolonged hunting or territorial life. They exist primarily to locate a female in the vast darkness of the deep ocean. And in that environment, finding one may happen only once. The deep midwater contains immense distances between individuals. Unlike shallow reefs or coastal ecosystems crowded with life, the bathypelagic zone often feels almost empty. A male anglerfish drifting through darkness may spend his entire existence searching for the faint chemical signature of a female somewhere in the surrounding water. When he finally finds her, he bites. His jaws clamp onto the female's skin, usually near her abdomen or flank. Then something extraordinary begins. Enzymes gradually dissolve the tissues separating their bodies. Blood vessels merge together. Circulatory systems connect. Over time, the male loses nearly every organ except the testes. His eyes degenerate. Internal structures atrophy. Nutrients pass directly from the female's bloodstream into his remaining tissues. Eventually, he becomes less an independent animal than a permanent reproductive extension attached to the female's body. Some females carry several fused males simultaneously, each reduced to little more than functioning gonadal tissue nourished through the shared circulation. Biologists describe this adaptation as sexual parasitism, though the term barely captures how complete the merger becomes. The strategy evolved because the deep ocean transforms mate location into one of the most difficult problems in animal biology. Encounters between males and females may be so rare that losing a mate after finding one could mean reproductive failure for life. Fusion solves the problem permanently. The female never needs to search again. The male never risks starvation while attempting to continue alone through the darkness. Two separate vertebrates become one functioning reproductive system drifting together through the deep sea. Far below the surface world, where light itself had to be reinvented chemically, Even reproduction followed evolutionary pathways almost unimaginable in the brighter oceans above. For more than a century, the colossal squid existed mostly as absence, fragments of flesh recovered from sperm whale stomachs, detached arms tangled in fishing lines, circular scars etched across whale skin after encounters deep below the surface. The animal itself remained almost entirely unseen, hidden within cold southern ocean waters far beneath ordinary observation. Then, in 2025, cameras finally captured one alive in its natural habitat. The footage showed a juvenile drifting through dark water, less than a meter long, its translucent body suspended with slow, controlled movement in the deep southern ocean. It did not resemble the gigantic sea monsters imagined in earlier centuries. It appeared delicate, almost unfinished, carrying within it the early form of one of the largest invertebrates ever known. Adult colossal squid are estimated to reach lengths approaching 14 meters and may outweigh every other invertebrate species on Earth. Their arms carry not only suckers but rotating hooks, hardened claw-like structures capable of swiveling independently as they seize prey. Unlike the smooth, gripping surfaces found on most squid tentacles, these hooks seem built for violent resistance within the dark, pressure-filled depths. Their eyes are even more extraordinary. A fully grown colossal squid may possess eyes nearly 30 centimeters across, the largest known in any living animal. In the deep midwater, where sunlight no longer penetrates and bioluminescent flashes become one of the only visible signals remaining, large eyes offer a critical advantage. Researchers believe the colossal squid evolved these enormous visual organs partly to detect distant movements made by hunting sperm whales, particularly the brief disturbances and flashes produced as massive predators move through darkness nearby. The relationship between squid and sperm whales has been written silently across the ocean for millions of years. Whales hauled to the surface often bear circular scars across their heads and bodies, evidence of encounters with giant squid fought far below human sight. The scars match the dimensions and arrangement of squid hooks and suckers precisely. Somewhere in the midnight waters, battles unfold between the largest predatory whale and the largest predatory invertebrate, both navigating darkness thousands of meters beneath the surface. Until very recently, no human being had ever directly witnessed those encounters alive. Yet, even the colossal squid is not the longest organism drifting through the deep midwater. Far from the seafloor, suspended within the water column itself, siphonophores extend through the darkness with astonishing scale. At first glance, they resemble single animals, long gelatinous bodies trailing through black water. In reality, each siphonophore is a colony composed of thousands of genetically identical individuals called zooids, all connected into one coordinated organism. Each zooid performs only a specialized role. Some handle feeding, others manage reproduction, some provide locomotion, while others carry defensive stinging cells. Individually, many zooids could not survive independently. Together, they function as a single integrated life form moving through the deep ocean as though composed of distributed organs rather than separate creatures. Among them, Priadubia reaches especially extraordinary lengths. Individuals may extend for 40 meters or more through the water column, potentially making them the longest animals on Earth. Their translucent bodies drift almost invisibly beneath the darkness, while curtains of stinging tentacles spread outward through the surrounding water. Unlike active predators pursuing prey across open distance, giant siphonophores often rely on patience. Their tentacles remain suspended through the water column like vast suspended nets. Small fish, crustaceans, and drifting organisms passing through the curtain become entangled among thousands of specialized stinging cells distributed along the colony. The deep midwater allows scale to emerge in unusual ways. Some animals grow massive through muscular predation and powerful sensory organs. Others achieve enormous size through colonial cooperation, thousands of smaller living units functioning together as one drifting body. Both strategies persist in darkness, where visibility remains limited and energy must be gathered carefully across immense volumes of water. Beneath the surface oceans of Earth, entire giants continue moving unseen through the midnight zone, their lives unfolding in cold black water that human eyes entered only recently. Despite these organisms having existed there long before the first ships crossed the sea above, long after the soft tissue of a whale has vanished from the seafloor, the skeleton remains behind in the darkness, pale ribs and vertebrae resting across the sediment, while chemistry continues slowly inside the bones. Oils trapped deep within the structure leak outward over years and decades, feeding bacterial communities that transform the carcass into a lasting chemosynthetic habitat. It is during this sulfophilic phase that another organism appears. At first glance, Osedax worms seem almost delicate. Thin red plumes rise from the surface of whale bones, like small flowers rooted directly into the skeleton. They sway gently in the surrounding water, only a few centimeters long, soft-bodied and motionless against the pale remains beneath them. Yet underneath the bone surface, the animal extends into something far stranger. Osedax, whose name translates roughly as bone devourer, was first described scientifically in 2004 after researchers examining a gray whale skeleton in Monterey Canyon discovered dense colonies attached to the bones nearly 3 kilometers beneath the Pacific surface. The worms belonged to the polychaetes, a large group of segmented marine worms, but almost every aspect of their biology appeared unusual. They possessed no mouth, no stomach, no digestive tract at all. Instead of feeding conventionally, female Osedax worms extend branching root-like structures directly into the whalebone itself. These tissues release acid capable of dissolving the mineral matrix surrounding the lipids stored within the skeleton. As the bone softens chemically, oils become accessible inside the porous interior. Living within those root tissues are symbiotic bacteria that process the released compounds and provide nutrients directly to the worm. Once again, deep ocean evolution returned to the same solution seen at vents, cold seeps, and whale falls throughout the abyss, animals surviving through intimate partnerships with microbial chemistry. The visible red plumes extending above the bone function largely in respiration, absorbing oxygen from the surrounding seawater, while the hidden roots continue dissolving the skeleton below. And even this was only part of the strangeness. Inside the body of each female live her males. Male Osedax worms are microscopic, often measuring only a few dozen micrometers in length. They never develop into fully independent organisms. After settling onto a female, they remain inside small chambers within her body for the rest of their lives, producing sperm continuously while depending entirely on the female for survival. A single female may contain dozens of males simultaneously, all living permanently within her tissues. The contrast between the sexes becomes almost surreal. The female grows large enough to be visible against the whale skeleton, extending red plumes into the water above. The males remain tiny internal companions, reduced almost entirely to reproductive function in a world where locating another individual on the deep seafloor may be exceptionally difficult. Since their discovery, Osedax worms have appeared in far more places than researchers first expected. Species have now been documented feeding on fish bones, turtle shells, and even ancient crocodile remains resting on the seafloor. Any large vertebrate skeleton descending into deep water potentially becomes habitat. The worms themselves appear ancient. Fossilized whale bones, dating back tens of millions of years, contain characteristic borings matching modern Osedax activity, narrow tunnels etched through the skeleton by root tissues dissolving bone from within. Some fossil traces predate modern whales entirely, suggesting that ancestral Osedax lineages may once have fed upon the carcasses of giant marine reptiles or primitive early whales long vanished from Earth's oceans. For immense stretches of evolutionary time, these worms have waited quietly on the seafloor for large bodies to sink from above. Their existence transforms even bone into temporary habitat and chemical resource. Nothing descending into the abyss remains untouched forever. Flesh feeds scavengers, oils feed microbes. Skeletons feed worms with no mouths and no stomachs, dissolving calcium and lipids, molecule by molecule in darkness beneath kilometers of water. The whale fall does not simply decay. It is consumed layer by layer, life passing continuously into other forms of life until almost nothing remains except drifting sediment and the faint chemical traces left behind on the seafloor. For most of animal history, the sponge body plan changed very little. Water entered through thousands of microscopic pores, passed through internal chambers lined with specialized cells, and exited carrying away waste while tiny suspended particles remained trapped behind. It was a slow and passive existence, one that emerged more than 500 million years ago and endured through nearly every major transformation in Earth's oceans. Then the deep sea altered the equation. Far below the reach of sunlight, on stretches of seafloor where organic particles drift downward only in thin intermittent traces, some sponges encountered a problem that filtration alone could no longer solve. There simply was not enough dissolved food moving through the water to sustain the ordinary architecture that had supported their relatives for immense spans of evolutionary time. And so several unrelated sponge lineages abandoned passive feeding entirely. They became predators. Carnivorous sponges do not resemble the branching reef sponges familiar from shallow tropical seas. Many appear delicate, almost skeletal, extending thin arms or filaments outward into the water column like carefully arranged traps. They remain motionless against rock or sediment, while small crustaceans drift nearby in the darkness. The genus Cladorhiza became one of the clearest examples of this transformation. Species within the group evolved specialized filaments coated in microscopic hooks, structures functioning almost like biological Velcro. Tiny amphipods and other drifting crustaceans brush against these surfaces and become trapped immediately, unable to free themselves once entangled among the hooked projections. The sponge does not rush toward its prey. Nothing in its biology allows rapid movement. Instead, the surrounding cells begin an extraordinarily slow process of engulfment. Tissue spreads gradually across the captured animal until the prey disappears beneath the sponge surface entirely. Digestion unfolds externally over days or even weeks. In shallow water, such behavior would seem unnecessary, an inefficient strategy compared with active hunting or continuous filter feeding. But in the deep ocean, where meals may arrive rarely and unpredictably, the ability to secure even a single crustacean can determine survival. Among the strangest of these predators is the harp sponge, Chondrocladia lyra, first identified off the California coast in 2012 at depths exceeding 3 kilometers. Rising upward from the sea floor, its structure resembles an elaborate musical instrument, Multiple vertical veins extend from a central stalk, each lined with dense, hooked filaments designed to intercept drifting prey. Seen in submersible lights, the animal appears almost architectural, less like an organism than a carefully constructed framework standing alone in the dark water. Yet every surface participates in predation. Tiny crustaceans colliding with the filaments become immobilized, and the sponge slowly absorbs them into itself, one by one. What makes carnivorous sponges especially significant is that this transformation occurred independently, multiple times. At least 3 separate sponge lineages evolved predatory, feeding through convergent evolution, arriving at similar solutions despite distant ancestry. The same environmental pressure, severe food scarcity in deep water, repeatedly pushed unrelated organisms toward the same biological strategy. The abyss does not merely shape life through violence or extremity. It shapes life through absence, through long stretches of emptiness where energy becomes precious enough to redirect ancient evolutionary pathways. Carnivorous sponges have now been documented at extraordinary depths, including nearly 9 kilometers beneath the ocean surface. During the recent Japan trench expedition that recorded hadal snailfish and supergiant amphipods, researchers also filmed predatory sponges fixed to trench walls deep within the hadal zone itself. Even there, where pressure reaches levels capable of deforming submarines and darkness remains permanent, the sponge body plan persists. Not unchanged, but adapted. The ancient filter feeder survived by becoming something else entirely, converting stillness into a hunting strategy and transforming drifting contact into capture. In the deep ocean, evolution repeatedly returns to the same quiet principle. No body plan remains permanent. No ecological role stays fixed forever. Even one of Earth's oldest and simplest animals can become a predator when the seafloor offers too little for gentleness alone. Long before drilling instruments reached deep into the oceanic crust, the seafloor itself was imagined as a boundary. Beneath it lay geology, heat, pressure, mineral transformation. Above it lay biology. The line separating the living world from the non-living one appeared clean and permanent. Then scientists began extracting cores from far below the sediment surface. Inside layers of compacted mud buried beneath kilometers of ocean water, and deeper still within fractures threading through volcanic basalt, they found cells. Not isolated contamination from the surface, but entire microbial communities existing in darkness, completely sealed away from sunlight and almost entirely disconnected from the rapid biological cycles of the upper ocean. The discovery expanded the boundaries of Earth's biosphere downward into the crust itself. This hidden realm is now called the marine deep biosphere. By area, it may be the largest habitat on the planet, extending beneath nearly the entire ocean floor across roughly 70% of Earth's surface. Every abyssal plain, every buried sediment basin, every fractured stretch of oceanic crust contains microscopic pore spaces where water moves slowly through rock and sediment, carrying dissolved chemicals that certain bacteria and archaea can exploit for energy. These organisms do not depend on photosynthesis. Many do not even depend on fresh organic material sinking from above. Their existence is tied instead to geological chemistry, to the gradual interaction between seawater and minerals deep underground. The pace of life there is almost impossible to compare with ordinary ecosystems. Near the surface, bacteria can divide in minutes or hours. In the subsea floor biosphere, some microbial populations appear to divide only once every 1,000 years, or even once every 10,000 years. Their metabolism operates so slowly that distinguishing living activity from ordinary chemistry requires extraordinarily sensitive instruments capable of detecting minute shifts in isotopes and molecular structure. There are cells beneath the seafloor that may have persisted through spans of time longer than recorded human history without reproducing more than a few times. Carbon dating revealed something equally strange: organic compounds being processed by some sub-seafloor microbes entered the ocean more than 11,000 years ago. In some locations, the carbon appears older still, remnants of biological material circulating through buried systems at speeds so slow they resemble geological processes rather than ecological ones. Nothing in this hidden biosphere moves quickly. Water seeps through cracks in basalt over immense periods, reacting with iron, sulfur, and other minerals. Chemical gradients emerge. Microbes harvest tiny amounts of energy from those reactions and endure in darkness beneath layers of sediment that may never again encounter open seawater. In 2015, researchers using remotely operated borehole observatories detected microbial concentrations approaching 100,000 cells per milliliter inside igneous crust itself. Not within soft mud or loose sediment, but within volcanic rock formed at ancient mid-ocean ridges and later buried beneath the sea. Life was inhabiting solid stone. The implications moved far beyond microbiology. Scientists studying the global carbon cycle realized the subseafloor biosphere may influence ocean chemistry on a planetary scale, slowly exporting ancient carbon-depleted organic matter back into surrounding waters. The deep biosphere was not merely surviving beneath the sea floor. It was participating in Earth's long-term chemical balance in ways only beginning to be understood. And unlike many surface ecosystems, this one appears astonishingly stable. Storms do not reach it. Seasons barely touch it. Ice ages pass overhead, while the microbial world below continues its nearly motionless existence among buried fractures and mineral grains. The ocean floor no longer appears as an ending. It is instead another threshold beneath which the planet continues breathing through microbial networks threaded invisibly through rock and sediment. The further science descends into the deep ocean, the less precise the boundary between biology and geology becomes. Water, stone, chemistry, and life begin to merge into the same slow system, operating across timescales so immense that even the deepest ocean above starts to feel temporary by comparison. The deeper science descends into the ocean, the less complete its maps become. Large animals can at least be filmed, collected, named, compared against museum records and evolutionary trees. Microbial life behaves differently. Entire worlds can exist inside a droplet of trench water, invisible until sequencing instruments begin translating fragments of genetic code into something faintly readable. And in the hadal zone, those translations increasingly lead into unfamiliar territory. During the MIR project, a large international research effort focused on the Mariana Trench, scientists gathered microbial samples from multiple depth layers extending through the trench system. Researchers from Shanghai Jiao Tong University, the University of Copenhagen, and Lawrence Berkeley National Laboratory compared the recovered genetic material against every major microbial database available. Almost 90% of what they found had never been documented before. Specifically, 89.4% of identified microbial species possessed no known scientific record. The number carried an unusual weight because the Mariana Trench is not an unexplored location hidden from study. It is the most famous trench on Earth, visited repeatedly for decades by submersibles, robotic vehicles, genomic surveys, and deep ocean expeditions. If any hadal environment could reasonably be considered well examined, it would be this one. Yet the overwhelming majority of microbial life there remained unknown. The finding altered the scale of scientific uncertainty itself. The hadal trenches were no longer simply remote ecosystems populated by difficult-to-study organisms. They appeared instead as immense reservoirs of undiscovered biology operating beneath the limits of existing classification systems. Each water sample contained genetic signatures belonging to organisms unlike those known from surface oceans, coastal sediments, hydrothermal vents, or ordinary abyssal plains. Some possessed metabolic pathways with no recognized equivalents in previously studied life forms, biochemical processes apparently adapted specifically for the crushing pressure, low temperature, and extreme nutrient limitation of trench environments. Even their genomes reflected the peculiar logic of the hadal world. The study revealed that evolutionary pressures in the trenches strongly favored two opposite survival strategies, with remarkably little between them. Some microbes evolved highly streamlined genomes, stripping away every non-essential gene in order to minimize energy consumption. Their biology became narrow, efficient, and specialized, conserving resources within an ecosystem where usable energy arrives only in sparse, irregular pulses from above. Others evolved in the opposite direction. These microbes carried unusually versatile genomes capable of metabolizing many different chemical compounds. Rather than specializing narrowly, they retained broad biochemical flexibility, allowing them to exploit whatever rare energy sources appeared within the trench environment. Very few occupied the middle ground. The hadal zone seemed to push evolution toward extremes, either radical efficiency or radical adaptability, as though the environment itself rejected compromise. And all of this unfolded at depths where sunlight has never penetrated, inside waters colder than polar seas, and beneath pressures capable of compressing steel. Some trench microbes appeared able to process dissolved compounds through pathways science still cannot fully reconstruct. Others carried genes associated with pressure resistance, unlike anything previously documented in surface organisms. The further sequencing progressed, the more the trench ecosystem resembled not an isolated branch of familiar biology, but a parallel microbial landscape shaped by entirely different constraints. There is something quietly disorienting about the scale of that ignorance. For centuries, the deep ocean was treated as biologically empty. Then it became biologically strange. Now, even after decades of exploration, its smallest inhabitants continue revealing that much of the living world remains uncatalogued. Not in some distant prehistoric era, but now. In the most studied trench on Earth, in 2025, nearly 90% of sampled microbial species were unknown to science. The hadal zone still holds entire evolutionary histories that have never been read. Beneath the trenches, within suspended particles of seawater and microscopic fractures in sediment, life continues experimenting in darkness, generating forms and chemistries that surface biology has not yet learned how to describe. At nearly 10 kilometers beneath the Pacific Ocean surface, the Mariana Trench floor was once imagined as the final biological limit for large animal life. Pressure there exceeds 1,000 atmospheres. Temperatures hover only slightly above freezing. Food drifting downward from the upper ocean arrives in sparse, fragmented traces after traveling through an immense column of darkness. For many years, scientists assumed that whatever larger organisms survived in such depths did so precariously, sustained almost entirely by the slow rain of marine snow from above. Then a Chinese research team descended into the trench in 2024 and found something else waiting in the sediment. Not isolated scavengers, not scattered animals surviving on occasional debris. A community. The submersible reached regions of the trench floor, approaching full ocean depth, and documented thriving colonies of tube worms nearly 30 centimeters long, alongside mollusks, crustaceans, and sea cucumbers clustered around fissures in the seabed. These were not transient visitors wandering through the trench. The arrangement of organisms, their density, and the surrounding chemistry all pointed toward a stable ecosystem operating continuously in the hadal darkness. The energy source came from below. Methane seeped upward through cracks in the trench floor, supporting chemosynthetic microbes that formed the foundation of the community. As at hydrothermal vents and cold seeps elsewhere in the ocean, bacteria converted chemical energy into organic matter, sustaining larger organisms entirely independent of sunlight. But this seep system existed at almost 10,000 meters depth, deeper than any comparable animal community ever directly observed. The discovery, published in Nature in 2025, altered assumptions that had persisted even after decades of deep ocean exploration. Chemosynthetic ecosystems were already known from vents and seeps scattered across the seafloor, but hadal trenches were generally viewed as biologically dependent on external input from surface waters. Organic particles drifted downward, carcasses occasionally descended, nutrients accumulated slowly within trench depressions. Now it became clear that at least some trench systems possessed internal energy sources of their own. The hadal zone was not merely receiving life from elsewhere. In places, it was generating ecosystems from geology and chemistry within the trench itself. That distinction carried enormous implications. If methane seep communities can persist near the deepest points of the ocean, then estimates of total hadal biomass may be profoundly incomplete. Entire networks of trench floor ecosystems could exist beyond the reach of current surveys, sustained by chemical processes operating beneath layers of sediment and fractured rock. The trench environment itself may be biologically richer than surface science long believed possible. There was also something symbolically striking about the organisms discovered there. Tube worms had once shattered scientific assumptions when they appeared clustered around hydrothermal vents in the late 1970s. Now, decades later, related forms were extending that boundary again, surviving at pressures once assumed incompatible with complex animal communities. The deeper humanity descends into the ocean, the further the limits of life continue retreating. And these discoveries are unfolding during a period of growing industrial attention toward the deep seabed. Nations and corporations are increasingly focused on the mineral wealth scattered across abyssal plains and trench environments, particularly polymetallic nodules and other resource deposits formed over immense geological timescales. The same regions once dismissed as barren are now viewed simultaneously as biological frontiers and economic targets. Each newly discovered ecosystem complicates that relationship. A trench floor that appears empty from the surface may contain slow-growing communities shaped over evolutionary periods far longer than human civilization itself. Chemosynthetic ecosystems operating in darkness near full ocean depth are not easily restored once disturbed. Many species discovered there may exist nowhere else on Earth. The Chinese submersible descent did more than extend a depth record. It revealed that even in the deepest known environments, life continues assembling itself around hidden energy sources beneath the sediment. At the very bottom of the ocean, where darkness, pressure, and isolation reach their greatest extremes, biology still finds pathways forward through chemistry and stone. For an unknown length of time, somewhere beneath the Antarctic ice shelf system, an entire seafloor ecosystem continued its existence without ever seeing open water above. No sunlight reached it. No seasonal bloom passed overhead. The ceiling above the ecosystem was not ocean surface but ice, thick enough to seal the region from the visible world for decades, perhaps centuries. Beneath that frozen barrier, life persisted in darkness, with no certainty that anything beyond the ice still existed at all. Then, in January of 2025, part of the barrier broke away. An iceberg, roughly the size of Chicago, detached from the Conger ice shelf, exposing a stretch of seafloor that had remained inaccessible beneath the Antarctic ice. Scientists aboard the research vessel Falkor, operated by the Schmidt Ocean Institute, moved quickly toward the newly revealed region before ocean currents and incoming species could significantly alter whatever had survived there in isolation. The expectation was cautionary and uncertain. Perhaps sparse microbial films, perhaps scattered invertebrates, adapted to low-energy conditions beneath the ice. Instead, the cameras descended into a mature ecosystem already fully established. Dense fields of anemones covered sections of the seabed. Sea spiders moved slowly across sediment, their leg spans extending wider than a human hand. Octopuses occupied crevices among rock formations. Icefish drifted through the dark water, their bodies carrying one of the strangest physiological adaptations among vertebrates on Earth. They possess no hemoglobin. In almost every vertebrate animal, hemoglobin gives blood its red color and transports oxygen through the body. Antarctic icefish abandoned it entirely during their evolution. Their blood appears nearly transparent, with oxygen dissolved directly into plasma instead. In the freezing oxygen-rich waters beneath Antarctic ice, this improbable strategy became viable, and it had remained viable here in complete isolation beneath the shelf. Researchers also documented organisms potentially new to science, species that may have evolved within conditions rarely encountered elsewhere on the planet. The ecosystem did not appear recently established or biologically fragile. It carried the structure of a long-functioning community, shaped gradually over extended periods beneath permanent ice cover. The question immediately became how such a system sustained itself. The energy source remains uncertain. Some scientists suspect chemosynthetic processes linked to geological activity or chemical gradients within sediment. Others consider the possibility that ancient organic material accumulated beneath the shelf may support slow-moving food webs over immense timescales. Research continues because the ecosystem does not fit neatly into earlier assumptions about the minimum conditions required for large, complex marine communities. What mattered immediately was the broader implication. For decades, planetary scientists have speculated about the subsurface oceans hidden beneath the icy shells of Jupiter's moon Europa and Saturn's moon Enceladus. Both worlds are believed to contain liquid water oceans trapped beneath kilometers of ice, possibly with hydrothermal activity occurring along their seafloors. The central uncertainty has always been whether isolated oceans without sunlight could sustain long-term ecosystems. Beneath Antarctica, Earth may already contain an analog. The newly exposed Antarctic seafloor demonstrated that complex marine communities can persist beneath thick ice barriers for extraordinarily long periods, while remaining entirely disconnected from any ordinary sunlit ocean. Environment. The ecosystem had not merely endured isolation, it had diversified within it. When expedition co-chief scientist Sasha Montelli described the descent, the words carried the atmosphere of genuine exploration rather than routine sampling. There was, she explained, a sense of entering a complete unknown. That sensation has accompanied nearly every major deep ocean discovery in recent decades. Again and again, environments once assumed empty or biologically impossible reveal communities already waiting there, operating quietly beyond ordinary observation. The Antarctic ecosystem extended that pattern into another hidden world beneath the ice. And somewhere, under the frozen crusts of distant moons orbiting the outer planets, there may be oceans holding the same silence, the same darkness, and perhaps the same slow persistence of life continuing unseen beneath kilometers of frozen water. Long before it received a name, the animal already existed quietly in the archives of deep ocean science. Its image appeared again and again in remotely operated vehicle footage from the Midnight Zone off the coast of California. A small drifting creature, nearly transparent, carrying a soft hood around its head and long tentacle-like structures trailing behind it through the water column. Along its body glowed points of blue-green light, faint but unmistakable against the surrounding dark. Researchers at the Monterey Bay Aquarium Research Institute encountered it repeatedly over more than 2 decades. They filmed it, logged it, compared it against known species. Nothing matched. The animal did not resemble the familiar nudibranchs of shallow reefs and tidal pools, those bright sea slugs crawling over coral and rock in sunlit water. This creature drifted freely in the open, deep ocean, gelatinous and fragile-looking, suspended thousands of meters below the surface, where pressure crushed ordinary forms into impossibility. For years it remained simply the mystery mollusk. Only in 2025 did the analysis finally resolve into something stranger than expected. The animal was indeed a nudibranch, a member of the sea slug lineage, but so anatomically distinct that it required the creation of an entirely new family. Scientists named it Bathydevius caudactylus. The name entered taxonomy quietly, yet it represented another widening of the known animal world. Not merely a new species, but a previously unrecognized evolutionary branch hidden in one of the most studied regions of the deep Pacific. Its biology carried the same strange elegance seen again and again in deep ocean life. When threatened, Bathydevius can detach its own tentacles. The severed structures continue writhing independently in the water, while their bioluminescent spots keep flashing through the dark. A predator pursuing movement and light may seize the drifting tentacles, while the nudibranch itself escapes into the surrounding water column. Among nudibranchs, this defensive strategy had never been documented before. The discovery revealed something deeper than the anatomy of a single animal. It illustrated the pace at which the deep ocean gives up its identities. The creature was not hidden inside an inaccessible trench or sealed beneath ancient rock. Scientists had already encountered it many times across decades. Its existence was visible. Its classification remained unresolved anyway. In the deep sea, observation alone is often not enough. Specimens must be collected without destroying fragile tissue. Genetic sequencing must be compared against incomplete databases. Morphology must be studied across developmental stages that may never have been observed together. Years pass inside laboratory analysis, while the animal itself continues drifting through darkness far below. And during the same period that Bathydevius finally received a name, other discoveries accumulated quietly beside it. Between 2024 and 2026, researchers analyzing material from the Clarion-Clipperton Zone described 14 entirely new deep-sea species of polychaetes, mollusks, and crustaceans. The region stretches across the Pacific abyssal plain between Hawaii and Mexico, an enormous seafloor province now attracting international attention for deep-sea mining because of its metal-rich polymetallic nodules scattered across the sediment. Within the same collections, scientists also identified 24 new amphipod species, including an entirely new family named Mirabestiidae and a new superfamily called Mirabestioidea. Entire evolutionary branches had existed unnoticed, inside samples already sitting in museum archives. Some specimens had been preserved for years before detailed analysis finally revealed what they were. The unknown was not always hiding in unreachable places. Sometimes it rested quietly inside storage drawers, waiting for enough time, enough expertise, and enough patience for someone to recognize that the tree of life was still unfinished. Far below the surface, the midnight zone continues carrying forms that biology has not yet learned how to name, organisms drifting slowly through darkness, while human understanding arrives only decades later, one careful classification at a time. Far from tropical shallows and the bright colors usually associated with coral reefs, there are forests in the deep ocean that grow in darkness so complete that no sunrise has ever touched them. They rise slowly from continental slopes, submarine ridges, and rocky escarpments between 200 and 2,000 meters below the surface. The water surrounding them hovers only a few degrees above freezing. Currents move steadily through their branches carrying tiny drifting particles, and in that perpetual cold, life accumulates grain by grain across spans of time longer than recorded human history. Cold water corals do not depend on sunlight. Unlike tropical reefs, they contain no photosynthetic algae living inside their tissues. They survive entirely by extending delicate tentacles into the passing current and capturing zooplankton, fragments of marine snow, and organic particles descending from the distant world above. Each feeding event is microscopic, each growth layer almost immeasurably thin. Some species add less than a millimeter of skeleton in an entire year, and yet over centuries, then millennia, those increments become architecture. Across the North Atlantic, the coral, once known as Lophelia pertusa, now reclassified as Desmophyllum pertusum, builds vast framework reefs that spread across the seafloor like pale stone thickets. Some of these reefs have grown continuously for more than 8,000 years, persisting through climatic shifts, changing ocean circulation, and the rise and fall of entire human civilizations far above them. Individual coral polyps within those reefs may live for several hundred years. Their calcium carbonate skeletons remain after death, providing attachment points for future generations. Slowly, the reef thickens outward, layers settling upon layer, creating an expanding three-dimensional structure inside what would otherwise be a comparatively featureless deep ocean landscape. And with structure comes abundance. More than 1,300 species have been documented, living in association with North Atlantic cold water coral reefs alone. Brittle stars coil through the branches. Crustaceans shelter in narrow crevices. Deep water fish patrol the outer edges. Microbial films spread across surfaces invisible to the human eye. Even in the deep ocean, complexity gathers wherever life is able to build something stable enough to endure. The reef becomes habitat not because it moves, but because it remains. Currents sweeping across these coral structures deliver oxygen and food continuously. Sediment is diverted. Larvae settle. Predators hunt along the margins, while smaller organisms disappear into the maze of branching skeletons. Over immense periods of time, The reef alters the surrounding ecology simply through persistence. In the hadal environments explored during the 2026 Japan Trench expedition, researchers observed another version of this same slow architecture. At depths approaching 9,300 meters, rocky outcrops supported dense meadows of crinoids, feather-like relatives of starfish attached to the substrate by slender stalks. More than 1,500 of them extended into the passing current together, filtering the sparse marine snow drifting downward through the trench water. The footage carried an almost unreal stillness, countless feathery arms opening and folding in synchrony, while the surrounding darkness remained motionless beyond them. Nothing in the deep ocean grows quickly without cost. Cold-water reef systems are especially vulnerable because their construction occurs on timescales almost incompatible with human industry. A single pass of bottom trawling gear can shatter structures that required thousands of years to assemble. Broken coral branches settle into sediment where regrowth may take centuries. Ocean acidification introduces another slower pressure. As atmospheric carbon dioxide dissolves into seawater, the chemistry shifts gradually toward greater acidity. Calcium carbonate skeletons become more difficult to maintain. In some regions, deep currents already carry water corrosive enough to begin dissolving exposed reef structures directly. Yet despite those pressures, the reefs remain where conditions still allow them to grow, continuing their patient accumulation in darkness beneath the open ocean. Stone by stone, polyp by polyp, a hidden architecture assembled in cold water over spans of time so large they almost cease to feel biological at all. At the deepest hydrothermal vents, where mineral-rich water erupts from the crust of the earth at temperatures capable of softening metal, there are living cells dividing calmly inside the flow, not surviving briefly, not entering dormancy, reproducing. The Archeon methane-powered candlery has been recorded replicating at 122 degrees Celsius, the highest confirmed temperature at which any organism has ever been observed, carrying out the full process of life. In laboratory conditions, most familiar biological molecules would unravel long before reaching such temperatures. Proteins lose their shape, membranes rupture, complex chemistry collapses into disorder. Yet inside vent systems, certain microorganisms remain stable because their entire molecular architecture evolved for exactly those conditions. Their enzymes fold differently. Their membranes contain unusual lipids that resist thermal breakdown. Even the proteins protecting their genetic material are adapted to heat intense enough to sterilize surgical equipment on the surface world above. Elsewhere, in the deep ocean, different organisms approach another physical boundary entirely. In the hadal trenches, pressure rises beyond 380 atmospheres, enough force to crush unprotected machinery and deform ordinary cellular structures. Many surface organisms exposed suddenly to such compression die because their membranes become rigid and their proteins cease functioning correctly. Barophiles, sometimes called piezophiles, do not merely tolerate that pressure, they require it. When brought to surface conditions, some deep-sea archaea and bacteria lose stability and die because their internal chemistry has become specifically tuned to crushing compression. Their enzymes flex properly only under immense weight. Their membranes maintain fluidity only when squeezed by kilometers of overlying ocean. To them, the surface is the hostile environment, and in the near-freezing water spread across abyssal plains and beneath Antarctic ice shelves, psychrophiles carry adaptation in another direction. These cold, loving organisms remain active at temperatures hovering around 2 degrees Celsius. Their proteins stay flexible despite conditions that would slow ordinary biochemical reactions almost to a halt. If warmed even slightly, some psychrophilic systems begin to fail. Life at the extremes reveals something unsettling about the way humans once defined habitability. For generations, moderate temperature, moderate pressure, oxygen-rich air, and liquid surface water were treated as the obvious requirements for biology. Those conditions shaped human experience, so they appeared universal. The deep ocean gradually dissolved that assumption. Again and again, organisms emerged from environments once considered sterile, proving that the familiar conditions of the surface are not laws of biology. They are simply one successful arrangement among many. The implications extend far beyond taxonomy. Extremophile enzymes already operate quietly inside modern civilization. Polymerase chain reaction, the laboratory technique underlying genetic analysis, forensic testing, and countless medical diagnostics, depends upon heat-stable enzymes derived from thermophilic bacteria discovered in geothermal environments related chemically to hydrothermal systems. Without those enzymes, repeated heating cycles during DNA amplification would destroy the biological machinery required for the process. The deep biosphere has become a source of industrial chemistry because its organisms have already solved problems human engineering still struggles to imitate: stability under heat, function under pressure, metabolism in toxic chemistry, persistence during extreme energy scarcity. Every extremophile carries molecular strategies refined across evolutionary timescales far older than human technology, and the catalog remains profoundly incomplete. Many deep-sea microorganisms still resist cultivation in laboratories because recreating their native environments precisely enough has proven extraordinarily difficult. Some survive only within exact combinations of pressure, mineral balance, acidity, and temperature that surface facilities struggle to maintain continuously. Genetic sequencing reveals metabolic pathways whose chemistry does not map cleanly onto known biological systems. The further exploration descends, the less exceptional extremophiles begin to appear. At some point, the pattern reverses. Moderate surface conditions no longer seem like the standard template for life, but one narrow ecological circumstance among countless others scattered across the planet. The deep ocean does not merely contain strange organisms. It contains alternative biochemical answers to the question of how living matter can exist at all, written into cells that flourish beneath crushing pressure, near boiling water, perpetual cold, and complete darkness, continuing their invisible work far below the conditions once thought necessary for life itself. There are maps of the moon more detailed than the maps of Earth's deep seafloor. That comparison appears almost impossible at first, because the ocean surrounds every continent, touches every coastline, shapes climate, weather, and chemistry across the entire planet. Yet most of the deep ocean floor remains visually unknown in a literal sense. No human eyes have seen it directly. No camera has passed above it. No biological survey has sampled it. In 2022, researchers attempted to estimate how much of the deep sea floor humanity had actually observed through submersibles, remotely operated vehicles, baited camera systems, and direct exploration. The answer approached absurdity: approximately 0.001%. The deep ocean floor covers roughly 335 million square kilometers, larger than the combined land area of every continent on Earth. Against that scale, The total area visually surveyed by human technology amounts to something comparable to a handful of city blocks scattered across an entire planet. Most of the abyss has never been visited even once, and within the tiny fraction already explored, new life appears constantly. Every expedition descending into previously unsurveyed terrain encounters species unknown to science, sometimes only one or two, sometimes dozens, occasionally hundreds. The pattern has become so consistent that absence of discovery would itself now seem unusual. The Ocean Census Project, launched in 2023, emerged partly in response to that overwhelming unknown. Its goal is to formally identify 1,000 new deep-sea species before the end of the decade, an objective that once might have sounded wildly ambitious. By 2025, researchers involved in the project already appeared well on pace to exceed it. Not because discoveries had accelerated artificially, but because the deep ocean continues producing unfamiliar biology faster than taxonomy can process it. One region in particular revealed the scale of the problem with unsettling clarity. The Clarion-Clipperton Zone stretches across a vast section of the Pacific abyssal plain between Hawaii and Mexico, an area rich in polymetallic nodules, now attracting industrial interest for future seabed mining. Between 2021 and 2025, scientific surveys sampling less than 1% of the region recovered more than 5,000 previously undocumented species. 5,000, and almost the entire zone still remains biologically unexamined. Many of those organisms are small invertebrates and microbes whose ecological roles are only beginning to be understood. Some may exist nowhere else on Earth. Others may participate in nutrient cycling, carbon storage, or sediment stability in ways invisible until removed. The difficulty is not simply that the biology remains incomplete. It is that industrial planning is beginning before the inventory itself exists. Even institutional language has started reflecting that uncertainty. The International Seabed Authority launched an initiative called 1,000 Reasons, a title carrying an unusually direct implication. The project acknowledges that humanity does not yet know what might disappear if large-scale industrial disturbance reaches ecosystems still largely undescribed. The challenge extends beyond scientific curiosity into logistics, almost geological in scale. Deep-sea exploration is extraordinarily expensive. Pressure-resistant submersibles, remotely operated vehicles, support ships, sonar systems, manipulator arms, and deep water sampling equipment require specialized engineering maintained by international teams. A single expedition may cost millions of dollars while surveying only a tiny fragment of the abyssal floor. Comprehensive mapping at meaningful biological resolution would require sustained global coordination across decades, perhaps centuries. And meanwhile, the discoveries continue accumulating faster than the maps. A trench wall sampled for microbes reveals unfamiliar metabolic chemistry. A baited camera lowered into darkness records amphipods unlike any previously cataloged species. A drifting mollusk spends decades unnamed in archived footage before genetic analysis reveals an entirely new family of life. The pattern repeats with almost unsettling consistency. Every descent adds organisms to the known world. Every recovered sample widens the evolutionary tree. Every newly surveyed landscape demonstrates that the deep ocean is not empty space waiting merely to be mapped, but a biological frontier so immense that even after generations of exploration, humanity has still seen only the faintest surface of what lives there, hidden across the overwhelming dark beneath the planet's oceans. Scattered across enormous regions of the abyssal seafloor are dark metallic stones that resemble abandoned fragments of another planet. They rest half buried in the sediment, sometimes isolated, sometimes spread so densely across the plain that the bottom appears paved with them. Most are roughly the size of potatoes, some are smaller than coins. Others grow as large as melons. They formed so slowly that human time barely applies to them at all. A polymetallic nodule may require millions of years simply to grow a few centimeters wider. Layer by layer, dissolved minerals drifting through seawater precipitate onto a central particle, perhaps a shell fragment or shark tooth buried long ago in abyssal sediment. Manganese accumulates. Nickel, copper, cobalt, rare earth elements essential to modern industry. The process unfolds with almost geological stillness among the slowest naturally occurring growth systems on Earth. And because the nodules contain metals critical for electric vehicle batteries, renewable energy infrastructure, and advanced electronics, they have become the focus of an accelerating international race toward the deep ocean floor. The Clarion-Clipperton Zone alone, stretching across a vast region of the Pacific between Hawaii and Mexico, is estimated to contain roughly 21 billion tons of polymetallic nodules. In terms of cobalt and nickel content, the deposit may exceed all currently known land-based reserves combined. For governments and corporations facing rising demand for battery technology, the attraction is obvious. Yet the nodules are not merely mineral deposits resting on empty ground. They are habitat. Across the abyssal plain, where soft sediment dominates most of the landscape, hard surfaces are extraordinarily valuable biologically. Xenophyophores anchor themselves against nodules. Carnivorous sponges rise from them. Brittle stars coil across their surfaces. Tiny invertebrates shelter in the thin boundary between stone and sediment. Microbial films spread across mineral layers invisible in ordinary light. Entire ecosystems organize themselves around objects growing at rates almost too slow to imagine. Remove the nodule, and the habitat disappears with it. Not temporarily, not for decades, for millions of years. A mining vehicle harvesting polymetallic nodules does not simply collect loose rocks from the seabed. It strips away the physical substrate, supporting communities that may never recover on meaningful biological timescales. Sediment plumes, generated by extraction machinery, drift outward through surrounding water, potentially smothering filter feeders and altering ecological systems, extending far beyond the mining site itself. And even now, understanding of those ecosystems remains profoundly incomplete. Between 2021 and 2025, scientific surveys in portions of the Clarion-Clipperton Zone recovered thousands of species previously unknown to science. Many existed only in single samples. Some may occupy highly restricted ranges linked specifically to local seafloor conditions. At the same time, larger animals unexpectedly entered the picture as well. A study published in 2024 found that whale and dolphin populations inhabit the waters above proposed mining regions in numbers far greater than previously understood. Migratory routes and feeding grounds overlap directly with areas targeted for industrial extraction. The abyssal plain below and the open ocean above, once studied separately, revealed themselves as parts of the same connected system. Meanwhile, negotiations continue through the International Seabed Authority, the organization responsible for regulating mineral activity in international waters. For more than a decade, nations, including China, the United States, Japan, and several European countries have debated the framework governing future extraction rights, environmental standards, and commercial access to the deep seabed. But the negotiations unfold faster than the biology can be documented. Researchers descend into these regions, attempting to catalog organisms before industrial machinery arrives. New species receive formal descriptions, while the habitats sustaining them are simultaneously being evaluated for commercial use. Museum collections expand alongside engineering proposals. The strange tension running through modern deep ocean science becomes difficult to ignore. Humanity discovered these ecosystems astonishingly late. Many were unknown within living memory. Some species received names only months ago. Yet already the pressure to industrialize the abyss is advancing ahead of complete understanding toward landscapes where evolution required millions of years to assemble communities that may disappear long before science fully learns what they were. Far beneath the Atlantic Ocean, around hydrothermal chimneys, hidden in permanent darkness, an idea quietly collapsed. For much of the 20th century, biology assumed that sunlight sat at the foundation of every living system. Even when animals hunted in darkness or plants decayed into soil, the chains still traced upward toward the Sunday photosynthesis appeared inseparable from life itself. A habitable world, therefore, seemed easy to define. It needed warmth, liquid water, and enough stellar radiation to sustain surface ecosystems. Then, in 1977, researchers descended to the Galapagos Rift and found entire biological communities flourishing around hydrothermal vents, completely isolated from sunlight. The discovery altered more than marine biology. It changed the mathematics of possibility. If life could survive through chemistry alone, drawing energy from reactions between rock and water deep beneath the ocean floor, then the universe suddenly contained far more potentially living environments than science had previously imagined. Distance from a star no longer represented an absolute boundary. A frozen surface no longer guaranteed a dead world below. The deep ocean had revealed another pathway. Since then, attention has increasingly turned outward toward the ice-covered moons of the outer solar system, places once dismissed as frozen wasteland. Europa, orbiting Jupiter far beyond Earth's warmth, now appears to contain a global liquid water ocean beneath an ice shell estimated to be between 10 and 30 kilometers thick. Gravitational forces from Jupiter continuously flex Europa's interior, generating heat through tidal friction. Measurements from spacecraft observations strongly suggest the presence of a rocky seafloor beneath the buried ocean, and many planetary scientists consider hydrothermal activity there highly likely. In nearly every measurable way currently available to observation, Europa resembles a scaled version of Earth's own deep ocean vent systems. Darkness above, liquid water below, internal heat generated through geology rather than sunlight. The resemblance becomes difficult to ignore. Even more striking is Saturn's moon, Enceladus. When the Cassini spacecraft passed through towering plumes erupting from fractures near Enceladus's south pole, it detected water vapor, ice grains, salts, organic compounds, and molecular hydrogen. That final detail carried enormous significance. On Earth, molecular hydrogen is produced naturally through serpentinization, the same geological reaction driving the white smoker ecosystems at Lost City, where seawater interacts chemically with mantle rock deep below the ocean floor. The chemistry associated with chemosynthetic life was no longer theoretical beyond Earth. It had already been observed. Somewhere beneath Enceladus's frozen crust, hidden beneath kilometers of ice and venting silently into space, An ocean appears to be interacting directly with warm rock. The moon radiates energy. Water circulates through mineral systems. Hydrogen accumulates. Conditions exist there that would once have sounded biologically impossible. And yet, Earth already contains living systems built around precisely those conditions. Farther outward still drifts Titan, Saturn's largest moon, wrapped in orange haze beneath an atmosphere thicker than Earth's own. Rivers flow there, rain falls there. Lakes gather across the surface, but the liquid is not water. Titan's temperature remains so cold that water behaves like stone, while methane and ethane flow as liquids across the landscape. For decades, Titan seemed too alien even for speculation. Now, some astrobiologists cautiously consider whether entirely different chemistries of life could operate there, using hydrocarbons instead of water as a solvent. At temperatures approaching -179 degrees Celsius, molecular reactions proceed extraordinarily slowly, and any hypothetical biology would function according to principles profoundly unfamiliar to terrestrial organisms. Science does not yet know how to search properly for such life, because all known biology emerged within the narrow chemistry of Earth's own environment. The deep ocean forced that humility into modern science. Again and again, beneath pressure once considered unsurvivable, inside acidic vent fluid, under Antarctic ice, within rock itself, or across trenches where sunlight has never reached, life continued, redefining the limits humans once believed were fixed. Each discovery widened the boundary slightly farther, and so the deep sea became more than an isolated ecosystem hidden beneath the waves. It became a working model for other worlds, a reminder that the universe may contain living systems in places humanity spent centuries overlooking, simply because the conditions did not resemble the surface of Earth. For hundreds of millions of years, the deep ocean floor has existed beyond sight. Continents shifted above it. Mountains rose and eroded away. Forests spread across the land and vanished again. Dinosaurs appeared, ruled the surface world, and disappeared into stone. Ice advanced and retreated across entire hemispheres. Human civilization emerged only in the final fraction of that timeline, brief and recent against the immense continuity below. All the while, in darkness deeper than night, life continued without interruption. Tube worms clustered around mineral chimneys that no human eye would witness for ages beyond counting. Snailfish drifted through trenches where pressure compressed every surface with relentless force. Xenophytophores spread themselves slowly across abyssal sediment. Microbial colonies persisted inside buried rock, metabolizing ancient chemistry grain by grain, century by century, in silence so complete it almost escapes description. None of it evolved for observation. None of it required recognition. The deep ocean never arranged itself for discovery in the way human stories often imagine. It does not conceal secrets intentionally, nor does it reveal them dramatically. Its ecosystems simply continue according to their own rhythms, independent of whether any surface species understands them. Reproduction continues. Predation continues. Cells divide. Organisms drift, feed, decay, and are consumed again, all beneath waters that absorb every trace of sunlight long before it can reach the seafloor. When a research submersible descends into the hadal trenches and its lights finally sweep across an animal that has spent its entire evolutionary history in darkness, the encounter carries an almost unsettling asymmetry. The human observers understand they are seeing something extraordinary. The animal does not. A hadal snailfish illuminated for the first time by artificial light shows no recognition of the event unfolding around it. There is no inherited memory of brightness there, no evolutionary context for floodlights descending through the black water. The fish continues swimming through the beam as though nothing unusual has happened, because within its world, nothing has. The machinery surrounding it, the cameras, the pressure spheres, the watching eyes inside them, all belong to another environment entirely, one as alien to the trench as the trench is to the surface. And still, from the tiny fraction humanity has managed to observe, understanding has already shifted profoundly. The discovery of hydrothermal vent ecosystems overturned assumptions about the dependence of life on sunlight. Extremophile biology redefined the limits of temperature, pressure, and chemistry compatible with living systems. Deep ocean microorganisms reshaped theories about the origins of life and expanded the search for biology beyond Earth. Enzymes, isolated from organisms adapted to extreme environments, entered laboratories and hospitals, becoming tools used quietly in medicine, genetics, and molecular science every day. All of that emerged from roughly 0.001% of the deep seafloor directly explored. The remaining 99.999% persists beyond observation, across abyssal plains larger than continents, inside trenches descending farther than mountains rise above sea level, beneath Antarctic ice shelves, within cracks in basalt hidden below sediment and seawater, around methane seeps and mineral chimneys that may continue venting long after modern nations disappear from history. Even now, while satellites circle the planet and telescopes examine galaxies billions of light years away, immense portions of Earth's own biosphere remain biologically undocumented. There are species alive in the deep ocean tonight that science has never recorded. There are metabolisms operating in darkness that no laboratory has reproduced. There are ecosystems unfolding slowly beneath the pressure of entire oceans, untouched by light, weather, or direct human presence. And perhaps the most unsettling part is how little the deep sea requires from the world above. It does not ask to be understood. It does not wait for interpretation. Far below the movement of ships and storms, beneath currents, beneath light, beneath the final reach of familiar life, the deep ocean continues exactly as it has for ages beyond memory. In the cold, in the pressure, in the dark, living